Hello, everyone. My name is Martinas, and today, together with my colleague Daniel, we are going to present the Kubernetes service load balancing implementation with BPF and XDP. This talk is going to be the, cannot change the, okay. 1 second, sorry guys. Ouch. It doesn't work. Maybe we should stop the webcam and.
Oh, sorry.
Okay, sorry, we had some technical difficulties. Anyway, so today's talk is going to be a continuation of the talk which was presented last year at Linux Plumbers 2019. So first of all, I'll give you an intro to the Kubernetes networking, and then Daniel will present our implementation and then a couple of suggestions for the BPF kernel extensions. Okay, so Kubernetes networking for kernel developers. So first of all, Kubernetes is a distributed container scheduler. The smallest scheduling unit is a pod, and for this presentation, it's enough to know that pod is basically an instance of a network namespace, and pod might run multiple containers. So basically, multiple containers can be running in the same network namespace. One important thing to mention is that Kubernetes doesn't network pods, and it's up to so-called CNI plugin to do all the networking for pods. And in this presentation, we'll be using Cilium as an example CNI because all the implementation which will be presented for load balancing has been done inside the context of Cilium. So Kubernetes doesn't provide any rules for the CNI plugins except the one that each pod has to be IP addressable and has to be reachable by this IP address inside the cluster, which means from a host network namespace or from any other pod network namespace. However, it doesn't say anything about accessing a pod from or service from outside the cluster. So let's look into a different scenarios how we can access a pod from inside the cluster. So the simplest one is by using a pod IP. So in this scenario, we have two nodes. Node 1 is running pod 1 and pod 2, and node 2 is running pod 3. And then we have an external client which is trying to connect to some service running on the pod 1. And pod 1 and pod 2 and pod 3 all belong to the same service. So client is sending a request to pod 1 by using an IP address. Everything works. We assume that both networks are pod network and the client network are interconnected. However, this approach has a huge disadvantage that Kubernetes doesn't guarantee us that pod will always have the same IP address, which means, for example, if a pod gets restarted, it might be assigned a different network IP address, which is a big no-go for us. Also, there is no built-in load balancing capabilities by using this access pattern. The next one is using so-called host port. So in this case, a pod has some host port assigned, which is exposed in the host network namespace on a host which is running that pod. So basically, when you create a pod object, you specify which host port to use. And this allows a client to use a node IP, which runs that pod plus host port to access the pod. So in this case, the client is sending a request to node 1 by using this 10,000 port. And once the host, which is running the pod, receives the request, it forwards that request to the pod. And before it forwards that request, it does the DNAT. So everything is fine except that with this approach, except that only one pod can ask for the same port. So which means that two pods cannot use the same port. So therefore, the usage is discouraged. The third one is node port. So node port is a bit similar to the previous example in the sense that some port is being exposed in the host network namespace, but this time multiple pods can ask for the same port, and this port is being exposed on all nodes which belong to Kubernetes cluster. So in this case, we have a client sending a request to a node 1 on that 30,001 port, and then once the node 1 receives that request, it does the load balancing decision. So if it selects the pod 1, it basically does the DNAT, it changes the packet's original request destination IP and port to the pod's IP and port which is listening on. And if the load balancing decision was made and it selected a remote pod, then what happens in addition to the DNAT, the SNAT has to be performed. So this has an advantage that multiple pods can participate in the service, and regardless whether the pod is local or remote. And also, basically, each node in the cluster, because it exposes the same port, each node is acting as a load balancer. And also, we can access such service from a host network namespace by using loopback address plus the node port. So we don't need to rely on DNS to do the name translation to a service, let's say IP or port. Okay, but this approach has big disadvantage. One disadvantage that majority of implementations are based on SNAT when the backend which is selected is a remote, and which means that the real client IP is not visible to a backend which receives a request. And also we introduce extra latency because a reply has to go back through the intermediate node which initially forwarded the request to the backend. The fourth way to access a service from outside is to use the external IPs. So if the cluster has an external IP available, which means that if at least one node is reachable by that external IP can be assigned to the service, and then the client can use that external IP to send a request to the service. So in this case, we have external IP, which is 1.1.1.1, and some port, which was set in the service definition. And once then, let's say that node 1 can listen on that IP address, can receive a request with this IP address, it will do the load balancing decision. So again, local case is simple. We just do a DNAT and send to a pod, and in the case of the remote backend being selected, we do it DNAT plus SNAT. So this approach is nice because basically we can impersonate any public IP address as long as that IP address can be used to access at least one node in the cluster. And unfortunately, the announcement of that IP address is completely up to network operators. So users have to run some special software to do that for. And one example how to announce is by using BGP. And also because the external IP is not, the setting of external IP is not managed in Kubernetes, it's completely up to a user to set that IP address. We cannot access a service from inside the cluster because then we open possibilities for man-in-the-middle attacks. Okay, then the fifth approach is to use so-called load balancer service. And this is, I'm going to show an example when a typical example when you run Kubernetes on-premise, not on a cloud provider. So in this case, you basically have a load balancer IP, which is assigned by some load balancing software running in the cluster. And this case is very similar to the external IP case because the access is being done by using the load balancer IP, which can be seen as an external IP plus port. And again, local case, we have a DNAT, and in the remote case, we have a DNAT plus SNAT. And one advantage is that this IP is being managed by Kubernetes, so basically users cannot set it by themselves. they cannot spoof traffic. And also the CNI plugins doesn't manage the load balancer IP and doesn't do any management for load balancer IPs and also for announcements. And usually if you run on cloud, each major public cloud provider provides load balancer implementation, and if you are running on premise, you have to install a load balancer by yourself. And the most common one is MetalOLB. So MetalOLB handles the IP address allocation and also the announcements of those IPs, and depending on the mode, it can use either ARP or NDP or PGP to announce the IPs. And one nice thing about MetalOLB that it doesn't sit in between client and the node, which is going to Kubernetes node, which is going to receive that request. So it basically doesn't sit in the critical fast path. Another case for the load balancer service is when a service is being provisioned on cloud. So in that case, you usually have a dedicated node which is doing load balancing, which means that the client first has to send the request to that node. And only then that node will forward a request to any of the node running in the cluster. And that node is using that load balancing node is using actually a node port to send a request to a node, Kubernetes node. So basically it means that when you create a load balancing service, you create a load balancing service plus node port service. And again, local case, so we have a pod which was selected and it's running in the same node as the request from the load balancer was received. And the second case is when the pod is being remote. So basically we have again DNAT and SNAT. Okay, so advantage that we don't have to install any special software in the cluster. Everything is done by cloud providers, so we don't have to take care of announcements. And also the cloud load balancers can do health checking for us, so it can detect which nodes are healthy, so to avoid sending a packet to an unavailable node. And the downside with this approach was that we have two layers of load balancing. So that dedicated load balancer node is doing the load balancing for us. Then it forwards a request to a Kubernetes node, and that node is also doing a load balancing. So we have two layers of load balancing. Also, cloud providers use load balancers of cloud providers are using some specific to them annotations, so which might not work when you migrate between different cloud providers, and also provisioning and programming of cloud providers load balancers can be slow. And for the sake of completion, we should mention cluster IP services. Those are basically services which are used to access pods from inside the cluster. So you cannot use the cluster IPs from outside the cluster. So in this case, we have a pod 1 accessing the pod 3, and it's using a virtual IP to access the pod. And that IP is from a defined range, from the cluster IP range, and that IP range is not non-routable. So it's only for in-cluster access. And besides that, as I mentioned before, that when you create a load balancer service, Kubernetes will create 3 services for us, so load balancer, node port, and cluster IP service. And when you create a node port service, Kubernetes will create a node port plus cluster IP service. And there are more features which I'm not going to mention, but which are relevant in the context of services. So, for example, session affinity and also external traffic policy, which we have implemented in Cilium. So, okay, I'm giving.
All right, and coming to Cilium's load balancer implementation and the lessons learned from that. Basically, Cilium's load balancer implements the data path in BPF for all the Kubernetes service types that we just heard of, and it does that by basically running a Cilium-specific pod on each node, and that pod has an agent on it that listens to events from the Kube API server, and the Kube API server basically tells the agent when new pods come up, new services come and go, and then it can basically reconfigure the BPF data plane. And the service implementation basically consists of two main components. One is that we run BPF at the socket layer and BPF at the XTP or TC layer, and both of them use the same shared service map, where we basically have the mappings from front end to back end. Coming first shortly to the socket load balancer, this basically handles all the east-west or in-cluster traffic. And it's basically implemented that it attaches BPF programs to different hooks for the socket, which is connect, send message, receive message, get peer name, and bind, and executes program there for doing the mapping or the reverse mapping. And so one of the issues that we saw, like, initially had is basically that Kubernetes still relies on cgroup v1, and there's cgroup v2 support in progress, but it's not there yet, and it probably will still take still some time to be there. And so the only thing we can do here in order to have like a hybrid model where we can attach BPF programs is to use the root cgroup v2, and that's why Cilium agent mounts its own cgroup v2 instance for doing just that. And the BPF, like the program logic for the connect and send message hook, is pretty much similar. It does the forward translation from front end to back end, and it does that based on the sock address structure. So there's no packet created yet at that point, so therefore we also don't have packet-based NAT, but based on the sock address structure and the receive message and get peer name, they are also similar in that they do the reverse mapping from the back end to the service IP, so that the application keeps thinking that it's actually connected to a service IP, which is in fact not, because we're connected to the backend. And that's basically done for TCP and UDP. And given we are at the socket layer, we also have to deal with not only v4 and v6, but v4 in v6 sockets, which is used by some frameworks, for example, the Java runtime and others. The service lookup itself is basically a scoped lookup. So that basically allows to have a different set of backends for some part of the services. Not all have this different set, so, but like a subset of it. And for example, for external traffic, when it comes into the machine, basically, depending on the service, we might only select local backends versus traffic that comes from the local node could select every backend, because it doesn't have to, in the end, go, for example, for node port services, it doesn't have to do the extra hop. And the lookup, there's also a wildcarded lookup that is useful for the socket load balancer and not for the one that is exposed to external traffic, because there we can access the service also for the loopback address or other local addresses, but this is not exposed to the outside. And yeah, basically that approach for the socket layer translation is super useful and helpful, because it allows to directly connect the socket to one of the backends without any extra hop in the network, which is, for example, done in the kubeproxy component by Kubernetes, which does this by default for node port services when backends are remote. And there's also a bind program that we attach, and that basically rejects bind requests if they are overlapping with services that are of node port type in the host namespace, so that there's no traffic injected in the middle. And two helpers were really crucial for that. One is the socket cookie, and the other one is the network namespace cookie. So plenty of cookies here. Socket cookie is basically, we use that mainly for the UDP sockets, so that for unconnected UDP, we always select the same backend for a given socket, and the network namespace cookie helper is crucial in two regards. One is that we can differentiate between the initial namespace and also the port namespace. For example, for the bind, so that we reject binds only for the host namespace. And it's also needed for so-called service session affinity, so that you will always select the same service backend for a given period of time. And given we don't have a source IP address for that part in this context, because the cgroup v2 program is not necessarily network namespace aware, we can make them aware with this helper and use that basically as a source identifier. So now to the north-south case for all the traffic that is coming into the machine, which is handled through the TC or XTP hook. And here, basically, the BPF side has to do a couple of things. First, the DNAT, so the mapping from the service to the backend, that is done on a packet level. And then also, when the backend is remote to that given node, we have to do either SNAT or DSR. That is also performed in BPF. There's multi-device support, which means that, for example, the device that is handling the outside world traffic is doing the translation, and then it has to forward it to a different device or network for forwarding the packet to the backend. And the other thing is the context abstraction that is done here, which I will talk a little bit in more detail later. And basically, the question that we were faced with when adding XTP support, because we had all the DNAT, SNAT, and so on implemented for the TC BPF side. So the question was whether we should somehow make the context more generic and abstract our program logic, or whether we should re-implement something minimal from scratch for XTP only. And basically, the way we decided is to refactor pretty much large parts of our code base from BPF to make it actually generic. And the rationale for that is that we avoid bit rotting. So the XTP side, at least for now, is not enabled by default, and optimizations that are done to the code in general can then apply to XTP and TC, which is useful. And just to show you some generic example code, so we basically have this CTX abstraction. And that basically, depending on the header files that get included, they have an SKP-specific implementation or an XTP-specific one. And so just one short, simple example. For the XTP case, we, for example, here map the CTX buff to the XTP metadata, and then also the return codes, they're generic and they're mapped to the underlying implementation. But with that, we also had the issue that we need to implement most of the used helpers that we have in the SKP context for XTP as inline functions, basically. And then LVM tends to optimize them because it sees the whole thing inlined. And yeah, so we had to make use of some inline assembly as a rescue for that. That's, for example, like one example how it looks. The XTP load bytes, we used basically this packet matching for data and data end. We had to hardcode this into assembly here in order for the verifier to recognize this pattern properly. And yeah, for the kernel itself, like 5.6 was actually, I would say, a major milestone, even though maybe it was not that obvious. But basically, that brought XTP for the masses, if you will, like on the public cloud, because it had support for AWS and Azure to ENA and the Hyper-V NetDriver, which is great. But if we want to have maximum support for a variety of drivers, the problem is that we can only rely on the bare minimum features that everyone implements so far in the networking side, which is XTP pass, drop, and XTP TX, which basically pushes the packet out the same device it came from. And from Cilium, we only support native XTP for the user-facing side, but we do use generic XTP as well, which is super useful for CI testing purposes. But the reason why we basically are not using the generic XTP is that given this load balancer runs in every end node in the cluster, it's just too much overhead for now to linearize every SKP and also to bypass GRO, which is not bypassed in the native case, actually. And coming back to the load bytes, store bytes, and other helpers, we when looking at the BPF disassembly, I also noticed that the built-in LVM functions, they are basically doing byte-wise operations. So we had to implement our own memcopy, zero, and compare and move helpers in the code base. That is simply because LVM doesn't have any specific context on other data that is not on stack. So for example, the packet data or map data. So it doesn't know exactly if so if the underlying architecture supports sufficient underlying access or not. Yeah, that's one thing. And also while benchmarking, we noticed that the K-time get an S helper has quite noticeable overhead on XTP side when there's high traffic load. And we basically optimize that by using BPF jiffies instead. So we have in the load balancer a BPF-based connection tracker, and that doesn't need like a high resolution. So switching that to BPF jiffies, if the underlying kernel supports it, is just fine for that. And it gave a nice speed up in terms of packet per second. Same for the CB, like the control buffer from SKP side. So we use that in the TC-based implementation. That's of course not available in XTP, and the first approach was to use the adjust metadata, but that has multiple downsides. One is of course the missing driver support, unfortunately, but also higher rate of cache misses that we noticed. And so basically switching to a per CPU scratch map instead for passing this data between tail calls gave also a noticeable speed up. Probably obvious in hindsight, but BPF map updates. So there were a couple of updates in the fast path that we had, and they showed up in terms of bucket spin lock. If the traffic comes in from multiple CPUs, and if the assumptions allow, this can be optimized basically in for the fast path case to have log3 lookup first, and if the element only if the element is not available or it's like mismatching the value, then we would call into the update instead. Flip lookup also came quite expensive, but given the XTP load balancer is basically hairpinning because of the XTP TX support, we moved that out, and it gave also a nice speed up of roughly 1.5 million packet per second in our testing environment. And last but not least, also to make sure that given all our tail calls that we have from the map side, they have static keys that are known at compilation time, that the LVM doesn't mess around with them and potentially add or like use different keys on different paths and then go to the map, to the helper call, where we would then end up in the JIT compiler emitting red booleans. We basically also implemented this as an inline assembly to really guarantee that this is not happening. And with that, doing a package gen test onto the Kubernetes node with XTP layer, we basically generated 10 million packets per second inbound and looked at how much we can handle for outbound traffic there. And the XTP side basically was able to handle all the incoming packet load and push it out of the node again for the remote backend case. And the TC side basically was only able to achieve maximum around 2.8 million packet per second, even though more or less the code implementation is the same, except for the BPF helpers, of course, compared to XTP. And the kubeproxy side, which is the default component shipped by Kubernetes, had around 2.4 million packet per second only. And the IPVS has slightly higher per packet overhead that we noticed. And the service here was just like one single service with one single backend used. Of course, the IPVS would scale better with more higher number of services, but it's still no comparison at all to the XTP case or TC1. And same for the software interrupt. So on the XTP layer, it's much less overhead in the software IQ processing for different packet rates we compared here from 1 million to 2 to 4 million packets per second. And at some point, like the TC or NetFilter implementation basically ends up spinning 99% in software IQ, and that's pretty much it. Yeah. So to some of the new kernel extensions that we're proposing, we're now looking at the path of where the backend is basically local when the packet comes in of the NIC and it goes through a local pod and it has to traverse the weave into a different namespace. Right now in Cilium, the case is that we have to basically push the packet up the stack, and the reasons why we do that are basically twofold. One is because there's the NetFilter implements the T-proxy for L7 proxies that is needed in our case. And the other one is that Kubernetes installs IP table rules by default, which drop invalid connections from the connection tracker point of view. And that was what happened in our case when we initially redirected the packet only on the TC layer from the NIC into the weave, but the reply traffic was going up the stack, and we had 8 asymmetric paths, and it was basically dropping. So that's why right now situation is, as you can currently see it here. But that also has the issue that replies from the pod, when they, like all the egress traffic, when it goes up the stack, then basically the socket gets orphaned from the socket buffer. And that's pretty bad, because it also has it also leads to missing back pressure at the QDISC layer when the packet goes out of the device. And yeah, so basically the BPF proxy work was merged some time ago into the kernel. So the last real dependency on NetFilter was removed with that. And what we can now do is like only stick to the TC layer. And there are basically 2 new helpers for redirection. And they borrow some ideas from the IP VLAN driver and bring them to the weave device, basically. One is for the egress traffic from the pod to XMIT into the neighboring subsystem, so all the L2 addresses are filled in, and then we can also retain the socket of the SKB, and that is basically done by the redirect neighbor helper. And the implementation roughly looks like this, that when we call this on the weave, on the host-facing weave on the TC ingress side, to push it out of the native device, it will basically do route lookup, and it will associate the dest entry with the SKB, and then it will call into the neighboring layer and to fill out the info, and then yeah, that will basically solve it. And the other way around for all the ingress traffic from the outside world would be like a fast ingress to ingress network namespace switch, and what that is basically done by BPF redirect peer. And what the implementation is on a high level doing, when this is called from the BPF program on the physical networking device on ingress, it will basically look up the destination weave here, and then it will basically retrieve the other peer and the other network namespace. It will then scrub the packet and set the device to the device inside the network namespace, and then do another round in the main receive loop. And it's not going to the CPU backlog queue. And the same thing is also really useful, the ingress to ingress switch. If the packet goes in from one local port to another local port, because we are already at the TC ingress layer in the host namespace, and we move this to the ingress into the other port. So, and the nice thing is that this also allows for trivial backward compatibility for all the kernels. So we can simply have the feature probe from BPF tool, and in the C code, basically, if those helpers are not available, use the old BPF redirect. So it goes normally through the weave XMIT case, and then does the network namespace switch. And for the redirect into the other, to the neighboring subsystem, we would still go, like for the old case, go up the stack from TC ingress side. And yeah, then we did a performance comparison to check the results, and basically on a TCP stream case, you can see here, like where my mouse pointer is, the maximum from the node to node case. They are basically connected back to back. And the current baseline for Cilium that we have, and with those 2 helpers, we get roughly plus 1.3 gigabit per second throughput. And the more interesting case is actually the TCP-RR. And currently the baseline for Cilium is around, on this particular setup, 8,500 transaction per second, and moving this up gets us really close to the node's maximum when NetPerf is running in both sides in the host namespace. And that basically gives a huge gain of roughly 2.9x more transaction per second. So yeah, with that said, please try out the kubeproxy free code if you want. And I've also put a link here for the POC code on the kernel side. I'm still cleaning it up, but it's basically working as it is. And yeah, so With that, I'll open up for questions. And I can already see one from Joe, whether the TC measurements were with the optimizations. Yes, so this was with the optimizations for the Solium 1.8 release. What minimum kernel version does XTP require? I would have to go back and check, but I think it's even pre-4.19. In the Solium case, we supported from 4.19 onwards, but it always, of course, depends on the driver support in the kernel for what driver you're using it and when that support was merged upstream. So on the cloud providers, it was like 5.6 onwards, but the Intel and Mellanox NICs, they supported like from the very beginning, the early days of XTP. Ah, there we go. So Paul says XTP itself 4.8. And then, yeah. Cool. Are there any other questions?
Hey, Daniel. Thank you for excellent presentation. Very informative. I've learned a lot. Quick question regarding the LLVM and tail calls. You mentioned something that you have to use the inline assembler, but I didn't quite get it. Like what LLVM, like what kind of issues LLVM is causing, why it would be indirect call instead of direct. So this is because like index will not be constant somehow from verifier point of view, or what?
So if the code is, if the BPF generated code somehow has like ends up at the same tail call, helper call, but it comes like it comes from two different paths with two different keys, for example, then basically the verifier will notice that and it will generate the red boolean instead, because it cannot guarantee that it's always the same static key in that case when we patch it.
I see. So it will be like two paths where the R3 register like has different values, but the call instruction is shared between those two paths.
Exactly. Yeah. That's the case. Yeah.
Oh, okay. That makes sense. Well, okay. Thanks.
Yeah. Yeah, also at some point we need to upstream into eBPF the LVM replacements, those built-in helpers. It's on the to-do list. We haven't gotten there yet, but.
And those, like you didn't mention the mem copy, right? So, well, you kind of mentioned, but you didn't show the code, right? So those on your still to-do list to upstream?
It's in the Solium upstream, but not yet on the BPF. You would need to do that. Actually, the nice thing about those helpers is that the size, at least in our case, like how much we want, it's always constant. Of course, it has to be. And for non-supported sizes, we basically throw a compilation error so that we can detect this and add this if needed. And it's actually the compilation error. I think it's like the LVM Clang translates this to intermediate code, but the compilation error happens because there's no mapping to the BPF backend for that specific built-in function, which is quite useful actually. But yeah. Cool. Are there any other questions? Please type now.
So one more thought. Like you listed a bunch of things that were, I think, new to me and to the audience. Like, do you think like it makes sense to start like tips and tricks sort of doc somewhere? I don't know. Maybe this one exists, like for the lookup and update, right? So the case when you were hitting the bucket log and you optimize it with like additional mem compare. That's that's pretty cool, right? So not sure how many people like have thought of it, but like all of these like little things, they seems to boost performance quite a bit.
Yeah, I definitely agree. I mean, usually those little things all add up, right? Yeah, so that was actually one of the purpose of this talk, but also I think I was wondering whether it would make sense to implement that for maps itself, maybe as an additional flag, but maybe it gets too confusing to users whether to use it or not. But documenting it in one way or another definitely makes sense. So, yeah. So, Tokyo says, yeah, please add the knowledge base. For example, XTP tutorials would make sense. I totally agree. Yeah. Cool. 5 minutes left in case somebody still has something. Otherwise, we can have a short break as well. Simon is typing, so let's wait. Or somewhere eBPF.io. Yeah, that would probably also make sense, or at least to link it from there. Okay, Willem is typing. Thanks so much for the memcopy trick. I was running into the same issue last week too. Ah, yeah, that's a good fit actually. So sounds like documentation is really needed. Okay, more docs. All right, so thanks a lot, everyone. We'll make a short break until 45, and then we continue with Marche's talk. So I just made you presenter, Marte, and at 45, feel free to start.
Okay. You can hear me?
Yeah, we can hear you fine.
Okay, I think it's 7:45, so we're going to start the next presentation. This is going to be a status update on the state of Android networking. And some of it's going to be about eBPF, but some of it's going to be about just Linux kernel networking in general. I'm Maciej Rzęczykowski, and I'm a developer on Android networking. And I should point out that last year at LPC 2019 in Lisbon, there was a similar talk at the Android Micro Conference. And here's a link to it. This is going to be both a refresh and an extension of that talk. That talk, because of being at the micro conference, wasn't on the networking BPF track, and I have a feeling a lot of people didn't attend. Hopefully, even if you were there, there's still enough new stuff here to keep you interested. So who I am, I've been at Google for quite a while, but I've only been working on Android for the last 2 years. So I still feel pretty new to all this stuff, and I'm still kind of discovering the state of the code base. I guess I could call it that. And my focus has been primarily on low-level stuff. So on kernel, on eBPF, on performance, on libraries, on command line utilities, low-level C code, basically. We have a relatively large team working on networking and on the kernel, but there's very few people that are actually working kind of on kernel networking. That's really basically just me and occasionally my manager, Lorenzo. There's a few other people that I would like to give shout-outs here. Alistair Delva for providing and helping with Cuttlefish Android VM. And of course, Greg KH for all his work on the stable trees, and Chenbo Feng for his work in the Android P and Q timeframe on and basically getting eBPF and Android started. And of course, Lorenzo, who's sponsoring all this work and making it happen and doing code reviews and that sort of stuff. Now, here's a disclaimer. Android networking is really, really big. Kernel networking is really, really big. And while we have a large number of people, the vast majority of them are working on the Java higher levels of the stack. Of people working on kernel networking, really there's just me, and even that's not really kernel networking because I'm spending most of my time working on user space. So a lot of effort goes into kind of uninteresting work, maintenance work, code cleanup, refactoring, keeping our tests passing, debugging various low-level problems. A lot of work also goes into basically helping OEMs debug stuff breaking as they're trying to upgrade to newer Android releases. And unfortunately, that means that there's not actually a lot of time left for future-facing feature development work. And that's kind of the problem with time, of course. But additionally to this, there's a standard kernel upgrade problem in the field. Even when we do kernel patches and kernel development work, the amount of time it takes to backport those changes and get those changes rolled out is, for all intents and purposes, infinite. So there's little immediate benefit. In practice, you can probably wait 3 years before you can depend on something, and another 2 or 3 before it really ends up in the hands of most users. So call it 5 or 6 years. This means that we're not really doing kernel development here so much as we're consuming upstream code and occasionally fixing minor bugs. That's particularly true for the kernel. The user space components, that is something that is relatively easy to upgrade from one Android release to the other. to the next Android release. It can still be problematic, but it's at least doable, while kernel upgrades are just infinitely difficult. As a result of this, eBPF is in a sense our savior, because it allows us to do things ahead of when we could do them if we had to modify the kernel. So here's a slide from last year about why we even do eBPF, and the reasons haven't really changed. Obviously, the core reason is to get rid of the code divergence from upstream Linux. We don't want to have to maintain local Android-specific networking patches. Performance, of course. I mean, that's probably the primary reason. And it's often more configurable as well. And as I mentioned, really the fundamental reason why we get pushed into this is we can't deploy kernel upgrades. We can potentially at least upgrade eBPF programs. It's still significantly harder than upgrading user space, but it's at least technically doable. And that was a slide from last year that I basically copied wholesale. This is a slide that is new this year, and having an extra year of hindsight, you know, I guess you could say the honeymoon is over. It's not all roses. eBPF is definitely an overall win, but it's really a win because we don't have an alternative approach. We can't upgrade kernels. So if you can't do something without a kernel upgrade, your only other possibility is either somehow do it with eBPF, or do it with only user space code, or just not implement the feature, or implement the feature only for newer devices. As for the specific problems that we have with eBPF, I think there's a fair number. I would say the first one is that it is actually very, very hard to write eBPF code. It is, at least in my opinion, it's significantly easier to write kernel code. In order to write the kernel code, you have to understand the network stack. In order to write BPF code, you have to understand the networking stack, and you have to understand the BPF additional code around BPF, and you have to understand the BPF helpers, and you have to understand the BPF verifier, and you have to deal with how the verifier rejects your codes and find workarounds, etc., etc., etc. So we write BPF code because it's the only thing we can do, not because it's really what we would like to be doing. We're also finding BPF to be really, really hard to debug. Crazy BPF verifier errors, packets not showing up in TCP dump, making debugging difficult. And also, you know, just kind of our own Android failure, where just our tooling that is available upstream, just not getting imported into the Android repository and just not being easily available on a phone. I find that this is a generic problem with Android, where just there's a lot of kind of standard Linux tooling that isn't generically available. And another thing is that eBPF still feels a little immature. I mean, it's amazing what you can do with it, but at the same time, very, very often you discover that the eBPF helper for something you want to do isn't available, or it's only available in a newer version of the kernel, and you're trying to develop something that will work on the phones that are actually available out there, and you're trying to make it work on a 4.9 kernel or a 4.14 kernel, etc. So this means that you end up kind of trying to find the common denominator, or you end up implementing multiple solutions depending on which kernel is present on the device. So, Android R hasn't even released yet. It's releasing soon, and it still has to support running on a 4.4 kernel. For example, the Pixel 2 runs on a 4.4 kernel, and we don't have BPF support at all. So we also need to have basically backup support code paths in user space to deal with that. That can be very, very painful. So now I'd like to move on to a summary of kind of what has been accomplished in the past couple years. Android Pie, that's basically 2 years old at this point, is where we first started using BPF. And this is primarily Chenbo's work. Here's kind of where you can already kind of see the problem. We require a Linux 4.9 kernel with kernel eBPF support, and that was theoretically a requirement of Android Pie for new devices. But we can only actually truly require it for all devices in Android S releasing next year. So you can kind of see the delay there. And Treble makes it easier for OEMs and device manufacturers to upgrade devices to newer releases of Android, but it also really ties our hands because we can't just add arbitrary requirements that, oh, you need to upgrade your kernel, oh, you need to add in, these additional patches, these additional features, you need to cherry pick this, you need to backport this, you need to enable this feature. None of that is possible with Treble. Basically, if a manufacturer launches a device with Android P on a kernel X, then they are able to upgrade to Q without even rebuilding the kernel. So nothing theoretically can change. So in terms of what we actually managed to accomplish in Android Pie, I think the primary win was the removal of the dependency on a custom Android kernel patch to netfilter for QTag UID to do basically bandwidth accounting. So that was replaced with BPF code. And the actual kernel functionality was only actually reverted next year in the Q era kernels. So there were talks in 2017 about this, so that's all I'm going to say about that. In Android 10 Q, which launched last year, the first thing we did was there was a paranoid Android kernel patch which basically blocked internet access for apps without privileges. We implemented this in eBPF with a requirement on a 4.14 kernel because we needed to use BPF C group hooks for this. And we reverted the patch out of the common kernels. And this is kind of where things get complex because it turns out that these patches can kind of come back from the dead even after you revert them because of the complex merge mechanism between different Android trees, where there's upstream, then there's the Android common kernel, and then there's the OEM kernels and the device kernels. So it turns out that I've ended up having to revert this code multiple times now. And another thing that we did in Android Q, which was a huge performance win, was we did IPv6 to IPv4 translation for cellular connectivity on IPv6 only networks. This was receive only, this was TCP and UDP non-fragmented packets only. So it was literally just kind of the most critical data path stuff. But it was a huge win because we basically moved this code from a user space daemon to BPF, and that was awesome. So that's Q. Right. So last year when I gave this presentation, I had a number of slides about what our plans were for Android 11, Android R. And I've copied these slides over wholesale, and I've basically taken the title plans for R and replaced it with plans for S, with the part in blue being what we've actually managed to accomplish. And as you can see, the answer is not a lot. It turns out to be very, very difficult. We wanted to do offload for CLAT, so for IPv6 to IPv4 translation, but in the opposite direction, for translation from IPv4 to IPv6. We managed to do that in the cellular direction. So when the upload is to a cellular link, we did not manage to pull that off when the uplink is a Wi-Fi connection on 4.9 devices because of a dependence on the Ethernet header. Basically, when you're uploading to a cellular connection, there actually is no Ethernet header. When you're receiving the packets from cell, it comes in as an L3 packet, and to transmit it to Wi-Fi, you have to add an Ethernet header. So depending in which direction you're transmitting these packets, you either have to remove the Ethernet header or you have to add the Ethernet header, and you have to do you basically have to figure out what the correct MAC addresses are. We were planning to handle IP fragments, ICMP packets, all sorts of other edge cases. We ended up not having time for that. We ended up spending a lot of time debugging various problems that we hit along the way. I'll talk about that a little bit later. So another thing we wanted to do in Android R is tethering offload, so that packets coming in on one interface that aren't destined for the phone can be redirected out another interface. And we managed to accomplish this unidirectionally for IPv6 to IPv6 only. That's the simple case that does not require NAT. Not in the uplink direction, sorry, downlink, uplink direction. Yeah. And we've started thinking about, what else could we do here that would actually provide a benefit? Because one of the fundamental problems here is that these aren't server class machines with relatively reliable performance profiles. It's actually very, very hard to do performance measurement work on a phone. There's tons of different clock domains that are constantly adjusting their CPU frequencies based on the available thermal profile of the device. Cooling is passive. If you run the device at the minimum frequencies, then you're not really representative of how it actually will be used in practice. If you don't do that, then the device immediately hits thermal limits and thermal throttles. So it's very hard to get reliable numbers. Additionally, to a large extent, you're actually more interested in power consumption than you are in raw throughput or raw packets per second numbers. And again, so much of that depends on parts that aren't the network. We were talking about, like, did you save 30 milliamps of power or did you not? When the entire device may be burning a watt or 2 watts. It makes it a really hard problem. We've been looking at maybe using XDP, thinking that it would probably provide us larger benefits than BPF out of the TC ingress hooks. But that's pretty exploratory at the moment. Right now, it looks like our initial assumption that the performance benefits would be from skipping the core stack are not really true. It is faster, but it is not much faster. The majority of the CPU power consumption is actually coming from very substandard drivers. And fixing those drivers is a huge problem because there's just so many of them on any given device. You've got cellular, you've got Wi-Fi, you've got Bluetooth, you've got USB, you've got various Ethernet dongles, you potentially even have Ethernet jacks. There's just so many of them. Another thing that we did pull off in Android 11 is we enabled BPF JIT, and actually it turns out that this works great on 64-bit kernels, but the BPF JIT on 32-bit kernels is actually not capable of compiling the code that we ship, so we had to backtrack out of it being enabled on 32-bit kernels. And one of the reasons that we didn't get all of that stuff that we had planned done is we ended up running into a problem where the BPF loader would randomly fail during the boot process. And it would fail sufficiently early that we didn't have any logs, and we would end up with random BPF programs that didn't load or BPF maps that didn't initialize. And many minutes later, some random interaction with the network stack on the device would crash. It would be something like you enable Wi-Fi and the phone tries to get bandwidth statistics and it discovers that some map that it wants to look at is missing and crashes. And it crashes in such a way that the kernel doesn't reboot. Instead, all the user space components reboot. And sometimes it just gets into a crash loop, and all the logs with useful data are long gone. And we spent forever trying to debug this, and ultimately, we ended up having to put a huge amount of work into our BPF loader to basically make it more reliable. And one of the major changes in Android R is actually the fact that the BPF loader now runs earlier during the boot process. It's considered critical in the sense that if it fails, the device will just reboot. And this means that the rest of the system can now actually depend on the BPF programs and maps always existing. However, in order to even do this, we had to actually make sure that all the BPF programs can be correctly loaded. And since we aren't necessarily 100% in control of the kernel, and this means that we actually needed to add some interesting functionality into the BPF loader. You can now tag, at least in the Android version of the BPF loader, you can now tag .os as being critical, so they have to load or BPF loader fails. And individual functions inside of these .os can be marked as optional. And individual functions can also specify a minimum and a maximum kernel version so that you can basically provide alternative implementations, making use of different BPF helpers depending on what is implemented for a given kernel. And potentially you can even provide multiple implementations for a certain kernel, and then they get loaded in order, and the first one that actually successfully loads is the one that you end up being able to use. So all of that was done to basically end up in a situation where you can say that the BPF loader should always successfully run to completion and successfully load all the BPF programs that match your device. We also added support for BPF maps and programs to have UID and group ID and permissions basically at the file system level when they get mapped into sysfs BPF, so that other non-root processes can potentially read or read-write these maps or make use of these programs. And it looks like we're probably going to have to take a look at extending this to also include some sort of SE Linux tagging. So anyway, that was R, and effectively that's also what's planned for S. It's pretty clear that there's way more there than we're actually going to be able to do. In particular, XDP is looking to be impossible. I'll talk about that a little bit later on. And now in S, we're finally going to be able to rely on the kernel at least supporting a minimal amount of BPF. So we're going to go in and actually clean up all our pre-BPF support code, which is going to be great. So as for the kernel itself, if you take the Android Common Kernel mainline branch and you carefully rip out the pieces that are network specific, it actually turns out that we're in a pretty good situation. You can see right now on screen the list of patches on top of 5.9 that are necessary, or even actually more than necessary, in order to get the networking test suite to pass. So as a refresher, Linus, releases the master kernel, and that gets pulled into stable LTS releases. And from there, that goes into Android Common. And Android Common has many branches. Basically, it's a multiplication of an LTS release times an Android OS level. And not all combinations are valid, but there's still a large number of these branches. These branches are used as the baseline by chipset or SoC vendors, Qualcomm, MediaTek, etc. And then those kernels, once they actually have hardware support added by the vendor, are actually picked up by OEMs in order to create the kernel for a specific phone. And this effectively means that there's a huge number of kernel trees. And because of this, it is very, very difficult to actually make a change across all Android kernels, because even just counting all Android kernels is not something I can do. This is technically improving year by year, but it is a very slow progress. As for the changes versus mainline, we have the networking test suite. Right now it runs on UML. There is an attempt to get it running based on QEMU. And as I said, we have 11 changes. 5 of them are actually to get a Cuttlefish Android VM based on QEMU running. They're relatively minor. The biggest change here is some virtualized Wi-Fi support in order to basically have a virtual machine with a virtual Wi-Fi card in it. Then we have 3 changes that are like 1 or 2 lines each. 2 of them are absolutely trivial. We just need to change some constants and remove an error return. These are basically places where Android and the upstream kernel differ in ABI, and it just kind of has to be this way. The third patch for NetBPF, permit redirect from ingress L3 to L2, is something that I tried upstreaming, and we didn't end up coming up with an ultimate decision about how to actually correctly fix this. This is still on my plate. In the meantime, we needed this functionality in R, and we had to go with a 2 or 3 line local patch in the Android common trees. So hopefully at some point we'll figure out how to actually correctly resolve this. Our real big kind of painful thing is we have 3 patches that are relatively large, relatively complex, and relatively poorly understood. The first one, I think, is the one that we have the best handle on, which is adding RA routes into per device tables. But then we also have 2 net filter patches that I don't even know how we make use of this functionality. I just know that it's necessary or stuff breaks. Yeah. So it's a goal to upstream our stuff, and we're really trying. And in R, we ended up just adding 1 patch with 3 lines. Unfortunately, we didn't really reduce our divergence by much. Although I know I owe Pablo some changes to idle timer, and as soon as I figure out what we actually need, I'll do that. At the moment, we have a mess. We tried getting quota to upstream. That turned out to be not trivial and ended up getting reverted. So hopefully we'll make another attempt at that at some point. And now kind of more open-ended stuff. So kind of where are the problems and things we'd like or would love to see. So first of all, security a huge problem. We have paranoid security people, and for good reason. I mean, people are trying to break into these phones and steal stuff, and there's a lot of hacking going on. And it's not only people trying to root their own phones, it's also a lot of apps and viruses trying to root other people's phones. So for this reason, there's a lot of requirements about being able to verify the eBPF programs that are getting loaded into the kernel. For this reason, the only thing in the system that is actually allowed to create and load BPF maps and programs is the BPF loader. It runs one time at boot and it terminates. Nothing else has sufficient BPF privileges from an SE Linux point of view, and it only loads these programs from a DM Verity partition. But it does mean that we cannot do any dynamically generated programs. All these programs are built at the time you build the Android OS. The only updates that the BPF loader does is the map updates in order to basically put in the file descriptor number of the map that it just created. And it also means that we can't even get constant updates in there. I know that there's been changes upstream to make arrays with constants better performance, but of course we don't have that in many of the kernels that we're actually running on these devices. We have a problem with filtering and or modifying netlink messages, where sometimes netlink messages are revealing privacy sensitive stuff like MAC addresses, and it would be nice if we could attach BPF programs to basically filter and zero this stuff out. I think ultimately this ended up getting solved in some other mechanism where basically this just isn't available to user space, but it's kind of sad and annoying that we had to do that. Another example is somewhere the stack generates U events based on, I don't know exactly based on what, but I know that there was some attempt to use BPF socket filters in order to basically filter out U events that were not interesting in order to prevent spurious wake-ups of the device, because that ends up being a battery draw, and basically it reduces the lifetime of your battery and your device. So making everything work on old kernels is really the fundamental problem here, right? Upstream is at 5.9. I still, ideally want to make things work on 4.9. Yeah, not much I can really do that. And the other one is, of course, there's a huge variance from device to device. As I said, I can't even count the number of kernel trees. Testing is a nightmare. Testing on a phone is a nightmare, and testing BPF is a nightmare. You multiply that out, and it just becomes almost impossible. Yeah, so I mentioned this a little bit, that because of the complex merge strategy, we can sometimes end up in situations where you revert a patch and it kind of just comes back as a result of someone somewhere thinking that it was dropped in error. And yeah, not much the open source community can do here. An interesting one that I ran into recently is we ended up with a boot time regression due to the BPF verifier being slow. And it turned out that a minor change to a program ended up drastically increasing the BPF loader runtime. Effectively, what seemed to be happening is that the BPF verifier in the kernel is basically running through the program, taking every possible, like from the beginning to the end of the program, every possible branch path. And as you add more and more ifs, the number of these branch paths is potentially 2 to the power of number of branches. And yeah, I added like 2 if statements, and suddenly the system was booting an extra 50 or 70 milliseconds slower, just because of how long it would take the verifier to test this. So it would be nice if there was some way to improve on the BPF verifier's time scaling aspect. I don't know exactly how. There's a generic problem with COVID making it harder to get access to devices, which has slowed everything down. There's another kind of interesting issue with eBPF, kind of poorly handling GSO frames. There seems to be all sorts of weird bugs in this area. The proto 4 to 6 and 6 to 4 conversion functions seem to suffer from curious bugs. I have a plan to send fixes for some of this upstream, but it's really hard to come up with a good cover letter to describe exactly what the problems are. Similarly, there's a lack of flexibility for translating v6 plus frag to v4 and back, because this involves the packet shrinking or increasing by 28 bytes, but the functions only adjust by 20. Ideally, we would further reduce the number of patches. It would be great if we could get some more of this stuff merged. I know that a lot of people frown at stuff like if Android, so I'm not actually expecting, but I can wish. Another problem is that sometimes we have these very simple feature patches that are almost like 1 or 2 lines in size, and it would be really nice if we could get these patches into LTS, because LTS is something that is significantly easier to manage than the Android common kernel trees. And yeah, basically, if it doesn't go into LTS, it's not really something I can depend on. Another one that's interesting is I would like to be able to use network namespaces and probably UTS and mount namespaces as well via netadmin, but without having sysadmin. So I don't know if people think this is a good idea or not. I've been thinking of sending a patch series for this. Another problem that we seem to constantly run into is that there just isn't enough bits in the mark field. So maybe at some point we should extend the mark to be 64 bits. Another possibility is maybe we need some sort of second mark field. I know that for 5G slicing, we're running into this problem again, where ideally we would be able to get applications to set some sort of application ID or something like a DSCP, but not actually the DSCP bits, just metadata, to allow the rest of the system to actually determine what the DSCP and other characteristics of that packet or connection should be. Another problem we have is right now, if you change the MAC address of an interface, that doesn't actually result when you bring the interface back up in the IPv6 privacy addresses being brand new, because they're not, in at least one of the address generation modes, they're not derived from the MAC address, they're derived from some random number that isn't reset when you change MAC addresses. So that's again something that we should fix upstream. Yeah, so another interesting one is it would be nice if we had some finer grained BPF attach privileges. Right now, you can basically either grant access to the BPF system call or not. You can't say that this process has the right to attach this sort of program to this hook or something along those lines. Similarly, I think we need SE Linux support on the BPF file system. It would be nice to have eBPF syscall filtering with argument inspection, especially as more and more system calls are taking pointers to flags, making basically the current BPF mechanisms not work. Anything to improve BPF performance would be great. The fact that BPF maps are statically sized is annoying. It would be really nice if these things auto-sized, or at least were resizable. Obviously, resizing a BPF map needs to be a separate privilege than creating one. There's also just a generic problem with eBPF support for dealing with IP or TCP header options. IP doesn't really matter, but TCP header options, if you want to do something like adv MSS clamp or receiver window updates or something along those lines, it's just painful. Another thing that I've run into myself is it would be nice if there was some sort of SKD verifier. You know, like you took a packet that was good, you ran it for a BPF program, it mutated that packet. Is the packet that came out, is it kosher? Are the offsets to all the various parts of the header set up correctly? Is the checksum correct, etc.? It's actually very hard to prove that a BPF program is actually correct for all the different types of offloads and checksums that the stack supports. We also have problems with regard to multi-threaded access into BPF maps. Right now, I think, like, for example, an ability to write to only part of a key would be useful, because right now we end up with places where we have to use one map, which is read by kernel, write by user space, and another map using the same key, which is the opposite way around. Because if you put that into the same map, you end up with unsolvable race conditions, at least as far as I can tell. And then kind of the last one, which is even less clear. I mean, we want a high-speed, low-power clat forwarding engine, right? That's what tethering is really all about. And the problem is we have tons and tons of devices and drivers. Cellular, Wi-Fi, Bluetooth, Ethernet, RNDIS, NCM, USB dongle drivers. I mean, dozens of drivers. A lot of these are entirely offload free. Some of them are actually non-GSO aggregating. For example, USB drivers will often receive 16 kilobytes of packets in a single buffer, and these packets are just back-to-back packets with nothing shared between them, and then they get mem-copied into actual SKBs. So if you try to use TC Act, which is the current approach we've been doing, you don't actually save on SKB alloc3 costs, you don't save on the mem copy. It doesn't really give you much above the core stack. If you were to implement XDP eBPF, that would be great, but there's just so many of the drivers that it's not really feasible. And really the only thing you want to do is you want to forward packets, and it's almost always going to be from a different driver to a different driver. So then you run into all these shared memory model problems. And I'm wondering if we could come up with some sort of lightweight XDP, which is perhaps not as efficient as the real XDP, but, you know, ultimately, like, for example, a transmit function that takes a pointer and a length and a pointer and a length. And that way we could eliminate some of these double, like right now, if you tether from a cellular link to a USB link, you potentially end up allocating 1.1 SKBs per packet you transfer and copying that packet twice. And maybe even, you know, multiple XDP programs, potentially 2 XDP programs on an interface. Here's a bunch of resources. It's really just AOSP code, nothing particularly surprising, I think. And questions?
So comment from Simon Hardy Francis. I have seen random XTP failures on Linux too, albeit not as serious as you described with the BPF loader, and detailed them in the XTP tutorial GitHub issue. So it's not just Android.
So our problem isn't XDP failing. Our problem is the BPF programs or the maps failing to create or to load. I don't know if that's exactly what he's describing. It sounds slightly different.
I was also wondering, for example, some things like the checksum validation. I think it's really hard also, like, especially for checksum complete, maybe. We should probably extend the BPF testing framework in the kernel to have some sort of validation, because we take SKPs from there and mangle them with BPF and then push the result back to user space, and maybe we should have some sort of facility for this sort of stuff as well.
Yeah, I don't have good answers. It's just something that I've always had issues with.
I'm going to make what's perhaps an unpopular comment. if I wanted to surmise your presentation, it would probably be like Android has a kernel update problem and it's getting worse, not better. I see an urge to look to BPF as a way to not have to deal with the kernel update problem that exists with Android, and I don't think that's a reasonable expectation, especially considering the fact that eBPF is a new technology and rapidly changing at the current point in time and hasn't really settled down yet. Also, yeah, it just seems like a lot of the problems that you run into are because you have the kernel update problem. And for example, you have to deal with, therefore, dozens of implementations of the BPF verifier and all the different quirks that exist there in those different versions. And you can't update it because of the OEM kernel dependency issues. And I just think you should rearrange your expectations to be more accurate considering the house that you've constructed with the Android.
Well, I mean,
situation.
David, I agree with what you're saying, but I think saying that it's the house we've constructed is also a little fake. I mean, this is basically just the state of the world in ARM, and it is improving, but very, very slowly.
Right. I just think that you've created a new set of dependencies now, since you have to have dozens of versions of your BPF programs and XDP implementations. It's just, it doesn't seem like a step forward to me. It seems a little bit of a step backward, especially in the situations where you have to have non-BPF implementations of a feature as well. That must be a maintenance nightmare of large proportion.
That theoretically goes away with time, right? I mean, eventually the old kernels die out and you end up with the kernels that support everything and you can just rely on BPF. But yeah, it takes years.
We have sort of a similar problem with Cilium, that we support everything from 4.9 onwards, but luckily distro distributions are updating more frequently, at least. Like 4.19 at least is a reasonable kernel to have your basic stuff working on. That's less painful, at least as an Android case, it seems. So.
Yeah, I mean, every kernel that's newer is better than the last one. 4.19 is better. Yes, I totally agree with this, but I mean, you know, the problem is that it takes about 2 years from when a LTS kernel gets released to the point when devices with that kernel actually make it out to the field. And even for the people working on these phones, we don't actually have these devices for development purposes in any kind of really usable form until relatively close to the public release.
I also noticed that there's a connection between the fact that we're independently now working upstream on adding explicit support for eBPF program signing, and it looks like Android did their own thing to validate the programs, the BPF programs that get loaded into Android. I think that's a good example of if Android had initiated work or ideas upstream, we could have maybe have been further along with the BPF program signing inside the kernel at this point.
I think you're overestimating what we did. DM Verity is upstream, so that's what is actually shipping the code. And the BPF loader is not large, and I mean it's basically using, you know, read an ELF file and load it into the kernel.
Okay, do you think you could make use of the BPF kernel-based BPF program signing in the future somehow?
I imagine so. I haven't looked at what that functionality is providing, but I believe that there are people that would like us to switch to that at some point, yes.
That's great. That's good news.
So, sorry, and switch actually is the wrong word to use here. We would not be switching to it. We would be extending the BPF loader that Android uses to also use that somehow.
All right. Nirav says the same challenge exists for folks who deploy multiple distros in their data centers. And I think there was a comment from Alexei, or you unmuted yourself, or?
I would say it very much depends on the data center.
Yeah, that's true. Okay, I think we're a little bit over time, so thanks a lot for your talk. And we continue at 9 a.m. Pacific time with John's talk. Thanks,
I
guys.
will just mention one more thing. I mean, deployment in a data center is a very different problem. It is significantly easier.
I agree. That's probably true, yeah. All right, so thanks a lot for your talk.
Thank you.
about now? Hello?
We can hear you.
Great, thanks. Does it sound okay? Volume's good?
Oh, good, yeah. Yeah.
All right, great, thanks.
Hey John, I just made you presenter, so feel free to start at 9 a.m. Pacific time.
Great, thanks. Yeah, the arrow key should work, maybe. Let's see. Ah, buttons work at least. Okay, I have 9 o'clock because we're ready to get going.
Yeah, please go ahead. Thanks.
All right, cool. Yeah, no problem. Sounds great. All right, well, first off, thanks for coming, everyone, this morning or evening, depending on where you're at. So my name's John Fastivant. I work on Psyllium and Linux kernel as well. And I'm going to talk about the topic today is right sizing is hard and resizable maps for optimal map size. But I think when I wrote this, I was must have been in a good mood and fairly optimistic when I wrote the abstract. So let's go to slide 2, and we'll say we'll change it a bit and say let's make it better map sizing, and we'll talk about kind of how that looks later here in the slides. But first, very quickly, oh, I think arrow keys aren't working. All right, so first, very quickly, it's sort of the agenda. So first, I just want to give kind of an overview of how I got to this problem and sort of the problems that I'm trying to solve with it. I think there's probably some related problems, but knowing my specific use cases, I think, and how I approach the problem will sort of be informative to the solution. And then we'll just talk a little bit about what we have today and the current situation that we're in. And then finally, I'll go through some work we did to do resizable maps for various types of maps, hash maps, arrays, and a few comments about self-map, although we've not actually done much work in that space. And then we'll wrap it up. And I have about, 30 minutes worth of slides, so should have plenty of time for questions. And okay. So first, Cilium is a kind of CNI plugin for Kubernetes, and recently has been added some host networking support as well. But that's sort of the Kubernetes side of things. What we need to look at for today primarily is just the data path, and I suspect this is sort of general, not just to sort of Kubernetes or cloud and container world, but generic for many types of data paths. But if we look at the Cilium data path, in this picture here on the left, we have the K8 pod. So this is just a pod, and the networking it has a network namespace and C groups and so on, and it's connected to the main networking through a VETH pair typically, or an IPVLAN. But in this case, in this picture, we're looking at a VETH pair for the normal case. And then the Cilium data path is going to run, and inside the Cilium data path, there's a bunch of different logic to do different things. And you can see in the boxes here, we have NAT and load balancing and connection tracking, sort of standard networking things that you would expect. And then we have some identity and policy and endpoints. So policy would be like your L3, L4, L7 policies. Identity is a way to map, sort of get stable mappings of identities from IP addresses and so on. So, but for this talk, the most probably interesting ones and the sort of the more general ones are the NAT, LB, and the connection tracking. And so we'll focus on those. Okay. And next slide. Great. So I presume most people are familiar with connection tracking, but here's sort of a simple view from Cilium side. Is every flow will have a state, and what we define a flow is can vary, but it's usually a tuple plus maybe a pod ID or an endpoint ID to sort of identify where that's coming from. And when you enter the first packet comes into the system, we mark it as new, and you have to do an update to a map. And then there'll be some number of in packets in the middle, and you'll need to do lookups to make sure that those packets are part of a connection. And then at some point, you'll get a last packet, and you'll identify that either by a flag in a TCP header, or a timeout in a UDP flow, or some criteria that you create, and then you'll do a delete from the map at that point. And so that's sort of a simple view, but it's good enough for when we're thinking about map usage case here. So Cilium for this has can either use an LRU or a hash map depending on the context that we're running in and what kernels. So on older kernels, we use a hash map. On newer kernels, we'll use an LRU. But this sort of creates a set of problems for us. What happens if the LRU overflows? So we might just remove possibly live flows, for example. What happens if the map update element fails in a hash map, which is sort of the equivalent of an LRU overflowing? So both cases in Cilium will just not insert the flow, and then you won't have a flow match when you try to do a NAT, for example, or reverse NAT, or a connection tracking state operation. So So these are both problematic. And so when we look at how do we build maps that match sort of the size of the system, there's multiple ways we can do this. And generally speaking, you come up with some heuristics based on how your garbage collection works. Is it an LRU or a hash map? How many CPUs are in the system? How much memory? How many nodes? How many pods? You can build, increasingly complex heuristics. But then you also need to account for worst case dynamics. So what happens if you all of a sudden get a burst of traffic, of not just traffic, but new flows, for example, in the connection tracking case? And one way to deal with this is you can overestimate. So you can say, well, I'll never have more than whatever in number of flows. So let me just overestimate. And if I hit that limit, well, dropping packets sort of is outside of the bounds of my criteria here. Unfortunately, this is not free if you're pre-allocating entries. So in Cilium, we're looking at 56 byte values. We have other cases for the connection tracker specifically, at least on the version that I was checking this out. I think it was master, so it may vary slightly across versions, but anyways, that's the rough ballpark. And then we also have other data structures where the values are even higher. So, 60 bytes to even larger values. And just the last point here is probably obvious, but dropping flows is not particularly nice, right? So you wonder why flows all of a sudden get dropped. This is one possible reason. So that's sort of how we get here. And we look at this and we say, well, how do we don't want to drop flows, and how do we get a right-sized map? And we have heuristics and worst case dynamics and all these things that are very difficult to sort of come up with a great answer to. So that's one use case. The other one we have in Cilium is we use sock map and sock hash. And if you're not familiar with this, this is a map that you can put sockets into. And it has sort of a couple different functions, but you can use it to apply policy at the socket layer. You can use it to do a sort of a glue two sockets together so that every time data is sent out one socket, it's received on another, or it's sent on another as well if you'd like to do that. Cilium can use this feature to do local connections as well. And the way that this works inside Cilium is after the three-way handshake happens, we have a sock ops hook, and inside that sock ops hook, we add the socket into this map. And at that point, we sort of glue the two sockets together, and we use our criteria to do that based on the policy that's in place from Cilium. One of the nice features about sock map and sock hash, though, is that the sockets are actually deleted automatically when the socket is unhashed by the kernel. So we don't have to worry about the delete case here. But we still have the same problems, like how many sockets are going to exist in the system. Okay, so we can choose, what Cilium does is we just choose some large number, and we hope that that's an overestimate, but not too large of an overestimate that we're wasting memory. And if the hash map, the sock hash fills up, well, it's not too bad because we just fall back to the normal path. So the sock hash case is a little bit nicer than sort of a connection tracking case or a NAT case where you don't do your NAT or you don't do your connection tracking and end up dropping packets. But on the flip side, it does create variation in performance, which can be hard to debug and understand. Right? So I was running, yesterday, and I had a latency of X, and then today, for some reason, it's twice that. So not particularly nice. It is a little bit nicer as far as the values. The values are just pointers, so it's not terrible to overestimate too badly here. And like I said, the drops are not fail. But that's just if we're using it as a performance optimization. As soon as you use sock hash or sock map to insert a policy, it suddenly becomes a critical component. And we can't, for example, not apply policy. So this puts it in the same space as like connection tracking, where if we can't fit the socket in the map, we must do something to the socket to make it no longer push traffic correctly. There are other use cases which are, we'll talk about as well, that Cilium doesn't necessarily implement, but load balancing is another case for this. So those are two cases where Cilium creates these maps which have to be sized to sort of match the system workloads. So, and then there's also the tracing use case that we bump into. So a system will have processes and sockets and all your other objects that you want to trace. Many of these kernel objects may not have upper bounds, or they have upper bounds that are fairly large, right? So, for example, if you get a GKE instance, you'll have a max PID of some 4 million max PIDs. So if you're going to create an object that maps to PIDs, and you want to handle the worst possible case, you would need 4 million of these. So pre-allocating 4 million slots is not reasonable for most value sizes, right? But similarly, we have process arguments, which can be quite large, especially if you're looking at Java applications. You might have pods, which you may not know how many ahead of time you're going to have, and sockets and so on. So there's all these different objects inside the kernel, and you might want to sort of keep data in a map that's attached to them or related to them. So there's been a lot of really good work, and we use it as well, to do things like have socket local storage, and there's some ongoing work for inode local storage. And the idea here is that you have storage, but it's actually associated with the kernel object itself. So that in the socket case, the socket storage will be associated with the socket, so you only ever use as much memory as you have sockets. And this is a really good way to get per socket storage without having to create a map and try to estimate what your upper bound will be. But on the other hand, it is tied to the socket. So if your use case needs that data outside of the socket lifetime, you need to have some way to get that data out and put it in somewhere else. Okay. So this gets us kind of in a similar state. And if it becomes a critical component, similar to sock map or connection tracking, you have the same case now where you need to ensure that the data is going to be available, because if you're using it for policy, you can't allow it to complete whatever the operation is to complete successfully. So those are three use cases that we've been looking at, so this got me to thinking about this, which is my sort of classic problem. On the memory side, I can pre-allocate everything, and I can overestimate everything, and I can use lots of memory. And that works well, and everything is nice and fast, because I don't have to do any allocations, but I am using lots of memory. And for very big data stores, this is sort of not tractable. On the other side, I can not pre-allocate anything, but now everything's going to be slower. So if I choose to pre-allocate, then I end up like something like this. This would be my good case. If I look at the usage, in the normal case, I want to use, so I'll start at the stable case actually. So in the stable case, I might have some set of entries in my map that are always being used. If I look at the x-axis here as slots in an array, for example, there might be a set that are always in use. And then there might be a set that are called the normal case, for example, in a connection tracker or something that's tracking processes that'll be created and deleted and created and deleted in the normal case. And those will just kind of come and go, and that's kind of a good usage pattern. And then there'll be a little bit of headroom on the edge case for things that go slightly over, and then eventually we'll go back into the normal case. So we keep this little buffer here for edge cases. And if this was always sort of my layout of how my map usage looked, I'd be quite happy. But usually, I end up doing things like this. I saw that the system had 8 cores or 16 cores or 64 cores, pick some number, and I thought this could probably do lots of I/O, for example. And so I have a map that's associated with some sort of I/O operation. And what happens is I allocate a big map, but that workload doesn't actually use much I/O because it's doing some other computationally expensive thing. And so I have all of this memory on the right side in my pre-allocated map that has slots, they have values, but they are never actually being used. So wasteful. And then sometimes I go the other way, and I have a small system that has maybe lots of I/O, and my normal case is using almost all of the memory. And so if I get any slight variation in the workload, I end up dropping packets or dropping I/O, tracking operations. So neither of these are ideal. But the next thing I did is I thought, well, I have a vague sense that pre-allocating entries is going to be faster, and I have a sort of a vague idea that allocating at whenever I add a value is going to be expensive. But I didn't have a great sense of what the actual numbers looked like. You can read the code and you can see the Alex, but the question is, what does the actual benchmark look like? So we created a benchmark, and we ran it here on a 12-core Xeon. And the benchmark, what it does is it takes different types of distributions of updates versus lookups, and it runs them in a for loop, basically. And so on the far left here, what you see is if I only ever did updates on my map, what would be the breakdown between a hash with no prealloc, an L or U, and a hash with prealloc? And what you see there is sort of the breakdown. And it falls to what you expect, right? You expect that, well, no prealloc is going to be pretty terrible because all you're doing is allocating. And prealloc should be fairly good because you have all you really need to do is find the hash and copy the values around. And in this particular benchmark here, you'll see at the top that the keys and the values are small. So it's a 4-byte key and a 4-byte value. So there's really not even that much copying going on. So then what was interesting to me is we kind of go up the thing. So we have a 50-50 mix, which is for every update you do a lookup. 25-75, so you do basically for every 100 operations, 25 of them are lookups and 75 of them are updates. And you keep going down, and you can see here. But I found kind of interesting. Go to the next slide. I think I skipped ahead myself a little bit. Oh, here we go. Is this one right here? It is the 1 out of every 99 mix. What's interesting here to me is my intuition would have said that the no prealloc would be slightly better. I still expected it to be worse, but not, what you're seeing here, the difference between the 22 and nearly 40, 39 or something, right? So not quite double, but 1.5 times better or something. So this I thought was interesting because this is telling me that even if I have a workload where updates are relatively rare, 1% of the time, I'm still suffering a performance problem in the no prealloc case. Okay. So and just to head off any questions. So first, I will post this to the benchmarks to the mailing list. These were written on top of the recently added bench work inside the self-test BPF. So the goal here for me would be to get these so that we can run them relatively easily and frequently and on different systems. So I'll add those. And the next thing that if you're observant here is that the updates and lookups are not analyzing the mischaracteristics. So in this case, we pre-populated the maps. And so we're not analyzing what happens when a lookup actually misses, which can have different characteristics depending on the map type. For hashes, it doesn't matter much, but we'll talk a little bit about where it can make differences later. So then the next question I thought would be, so that was 4-byte values. What happens if I have 50-byte values? Maybe the copy starts to have more impact and we see less difference between the different types. And the answer you can see here is, well, not really. You still have the same trend, even with a 50-byte value. Now we could bump that values up to 1K or 2K or whatever you would like, and I didn't do it here. But 50 bytes is the size of Cilium's connection tracker, so it was sort of a natural thing to look at. And what you'll see here as well, again, even at the 1 to 99 mix case, you see the same thing. It's better to pre-allocate and significantly worse to not pre-allocate. So in my case, my intuition was obvious down here. Updates are going to be painful, and was obvious up here in the lookups. It's going to be a slight difference. But in the middle, I sort of believed, oh, this was a little bit surprising that the difference was this wide, to me at least. So now the question is to pre-allocate or not to pre-allocate. So where we can, we don't have to pre-allocate. We can make the max entries much, much greater than the worst case. And this doesn't actually cost us anything other than if you talk about C group memory locks and stuff like that. But in general, it doesn't cost us that much. But where performance matters, we can't afford to do this, right? The connection trackers and policy engines that are running on top of sockets where we want to have good great connection times, so on. However, we want to avoid this large amounts of memories without having extensive knowledge of the workloads, because Cilium is quite tricky to know exactly what everyone's workloads are. Many times people don't even know, the team that's deploying Cilium may not know precisely what workloads they're running on. And we would like to grow the memory as needed. If we end up in a case where we underestimate the memory, we want to be able to sort of create more memory on the fly. So we ask the question is, can we grow the map when needed instead of drop new entries? And then we have these additional pieces that we would like. We'd like to only pre-allocate memory I need, and we'd like it to be fast. Unfortunately, this is a big wish list, right? This is, I want everything. So let's ask the slightly simpler question. Can we grow maps when we need to? And the answer to that is yes, and we'll talk about why. And what it costs us is a new error code, eBusy. So let's consider the hash resize. There's a slight note here about direct access on arrays, and we'll talk about that later as well. But let's talk about hash resize first. So what did I do? I created a new map type hash resize. It's backed by an rhash table object. It's been in the kernel for years, so it's quite stable. And it has these sort of characteristics. And I'm not going to go into exactly how our hash tables work here. It's a slightly different talk and would take longer than, if I added it here, it would take longer than the 40 minutes I have. But the gist of it from a locking standpoint is on lookups, we'll build lockless lookups. And then on updates, deletes, we'll need to lock buckets. And if there's a resize operation in progress, this is where we may get the busy or an again error. In different cases, give different errors to make it clear what's happening. But this is where your cost in doing this is that if you resize and you have an entry at the same time being added, you may have a busy error. So we took the sort of standard rhash table in the kernel, it's in /lib, and we started to work on it for BPF. So right now there's watermarks, so we added a BPF grow and we added a BPF shrink. These allow you to grow and shrink your map. Presumably as a BPF user, you have more insight into when you should be growing and shrinking your map than a generic watermark. But we kept the watermarks as well in case you want to use them. We kept an upper bound because if you're being DDoSed in your NAT table or your connection tracker, you don't want to grow endlessly. At some point you want to say stop and I'm going to drop packets because I'm being DDoSed. Used and combined with that, with the grow and the shrink, you can kind of create conditions to identify when DDoS is happening. You say, I only want to grow if I'm not seeing a bunch of send packets all in a row, for example, that indicate, all from one IP, or, pick your own criteria for what a DDoS is. We allow you to configure the initial limit, so you can set a max and then decide how big do you want your initial table to be. We moved a bunch of generics from the code. So right now, the /lib version of our rhash table is quite generic. It can be used for many, many use cases. But unfortunately, this comes at a cost from a performance standpoint. So we removed most of the general purpose stuff inside the rhash tables and made it very specific to BPF. we updated some of the error code. So if you're a BPF user, when you get an error code back from a map update, you have some idea of what happened. Was it sort of a mem error, or was it I'm in the middle of a resize operation and I should try again? And then there's just some general bits moving around. And again, just to reiterate, this is the new cost, right? Before, you would have not got this eBusy error unless the map was full. But now you have an eBusy, and now you're, as a user, you now have the new problem of what should I do when I get an eBusy? Should I retry? Should I wait? So, and this is a slight aside, but it's relevant because we're talking about maps. And the first point there is just that the benchmarks that we're going to see in a second are using hard-coded watermarks just for simplicity. But I also developed a map library that maintains statistics about the maps. So it'll tell you, presumably you could then use these to tell you when to grow and shrink the map. So they would track the current size of the map. We track the number of busy errors. We track the different types of errors and the frequency that we're getting them. And this is not done as like a helper or something outside. It's just done as a set of BPF, quote, BPF libraries. So if instead of doing a map update element, you could, for example, do a map lib update resize hash, and then you could get all of these statistics about how many entries are currently in the map, how many have been deleted, how many have been added, but kind of get usage characteristics about your map that you can also read out from user space and then report up. And this is quite useful because you might want to know, for example, when your map is being overrun, right? You have a hash table and you're dropping entries. Are you dropping entries for mem entry reasons, or because the hash table is full? These kinds of insights can give you some sense of how well your map sizing is actually doing. I'm going to talk a bit about this, but just to reiterate, this is the cost, and you have a couple of choices. You can do it again. How many retries you want to do is really up to you. You can drop the packet, but the assumption here is that this is better than, say, dropping all of your packets when you overrun the limit, or not being able to enforce your policy anymore because you have too many processes in the system, for example. So how did we do it? Or how did we do? Sorry. Let's look at some numbers because that will show us how we did. We have 4 cases here, and this is the same metrics again, starting on the left side from purely updates to all lookups on the right side. And if I, oops. Okay, so that build out didn't quite work in PDF, but that's all right. I'll just walk you through what each color means here. So the hash no prealloc, we know from before, is just a hash with no pre-allocated element. The hash in the blue here is your pre-allocated hash table. Both of these two exist. The yellow version, the hash resize right here, is a version of the hash resize that uses the /lib r hash table. So this is the characteristics you get if you use what's in the /lib. Okay, and then the hash resize plus underscore reuse, I can tell you what the underscore reuse is about, is the version that's optimized for BPF. And so what you see is on the updates, we actually do quite well in this case. And then if we go all the way over to the lookups, on the right side, we're doing about as good as the no prealloc. Slightly less, not quite as good as a hash table, but where things get interesting is in this mix range here, where you have 1 out of every 99 mix, for example. In this case, we do performance-wise, we do better than the no prealloc, and getting closer to the hash. And 10 to 90, or even the difference is quite low. As we go down, we get better. And so the takeaway here is you're getting performance that's better than the no prealloc, getting close to the hash with the prealloc. It's not one-to-one, but what you gain is the ability to grow your map. So in conclusion, so we have a resizable variant of hash table with good performance characteristics. We introduced this new error, but we think it's better than dropping packets on the floor. And the other thing to keep in mind is that those benchmarks are from sort of an initial implementation, right? That's a not terribly optimized case. I think there's probably room for optimizations inside the BPF RH table version. Okay, so that's the resize hash table. And then the next thing we did is we said, well, that's good for hash tables, but what about these arrays that we have running around? It'd be nice to be able to resize our arrays as well. And so what I did is I started to look at how to chain memory together. So you allocate your initial array, and then you run BPF grow. You somehow chain that memory and so on. You can grow it again and so on, and keep building more and more memory. And end up, what happened is you just end up doing pointer chasing. Okay. And I decided that that was horrible. The performance was bad. The code was clumsy. So we scratched that off the list. Don't do that. And well, the insight I had is that this is actually what I did was actually sort of a poor implementation of a map of array plus having arrays as the inner maps. So we already have this ability to have maps in maps, maps of maps, I guess. Maps of arrays we have, and we'll have arrays. So the question then I thought was, well, can we just build the resizable array based on what we have already today? And the answer is, I think so. We have a key, we have an array. This is what we'd like. We'd like the key entry to work. You say, I want key X. Here's my array. I look at this entry. So there you go. So then how we built this up is on the left side, we have the map of arrays. We have array 0, array 1, array 2. All pointing here. And we have a key X. And we want the key to look like a arbitrary offset. So we pick a slot, and then we can, using this sort of formula, we can figure out where it lands. Basically, because the array sizes are fixed, you can find the slot. By subtracting the offset from the slot, you can find the offset in the specific array. And now you can get the pointer, and once you have the pointer from the lookup, you can do the lookup inside that pointer to get the element using the offset. And this gets you something that looks like in the last slide where you have a contiguous array using sort of slices of arrays. So this is a sort of pictorially what you can visualize it as is a bunch of slices of arrays that are all glued together. We pretend it's a single array, write a wrapper around it to do this math, and then you get your sort of illusion of having a contiguous memory. Cost, of course, is this operation here. And you want to ask, so how does that look as a benchmark? Again, I'll add this to the bench's test framework and push it upstream here. So what we have here is different operations. The first one, I think if it shows up, this one did work. It's just a standard array. What if I just allocated one big contiguous array? It's not resizable because it's one giant array. And run a type for loop to get a benchmark around a lookup plus an update. So in this case, we didn't do the entire spread of operations, but we're just looking at a lookup plus an update, 50-50 split. That's what we get. And then just sort of round things out, we take this array of maps. We do a dereference on one of the maps, and then we just do a loop lookup update on that one. And about the same performance within the noise, which you would expect if you looked at the code, right? You do one lookup, and then you do a bunch of map updates and lookups. Same code as in the first case, should be equivalent. So then we have all of this series of the star 1, 2, 4, 8. So then the next question was, so what is the cost of that? What is the cost of doing that operation to find the subarray and then find the offset? And that's what you see here. You see it's, it's fairly, depending on your take, large or small. It depends on how critical you are of performance here and how much you would like to be able to resize things. But that's the gap. But the important piece here is that as you go from 1 to 2 to 4 to 8, and I stopped counting at then, but 16 as well, I should put up here, it also works. You see a flat trajectory. And we could go farther out to see how far this is going to, kind of stay this way. But at least initially, this looks like we're keeping a flat line. So it doesn't really matter how many times you extend it. And there's a quick question about, is this from user space or kernel space? So this is all from the BPF side. And the reason is mostly because almost all of the code that we're using in Cilium, the data path side is where we care about performance. See some typing, so interested to see questions here. Okay, so there's a question about powers of 2 and how to optimize for that, and the answer I'll talk about in just a second. There's definitely ways to do that for sure. Okay, so there's the obvious tricks. Like I think in one of the equations that I had a division, you obviously don't want to do division in your fast path. So that's pretty obvious. So one way to do it is use jump tables or just if-else cases. Those are pretty fast if you don't have too many subregions there. And then the other way is to just find ways to make your math easy, use powers of 2, so on, like that. And this is all to be done. I've sort of only got the simplest cases working, but I think there's some other ways to play with this, kind of how to make the math easy and how to get many slots available. There's another question on the list. I look at lib urcu and rcu lf hash. For RCU lookups, it implements lock-free updates and does not require the busy updates for concurrent with resize. No, I haven't looked at that. I just have only looked at the lib rsh hash table, so that's a good point. The one that's in the kernel specifically. So I'll take a look at those for sure. That's a good input. And then we also lost direct access when we did this, and I didn't have that on the benchmark. But if you have an array of size 1 element, we currently have this ability to do direct access, which we, instead of doing the call, you'll do inline assembly. So my plan then is to explore what that looks like with more than 1 entry. And then in theory, we can get rid of that multiple map update calls, map lookup calls. So right now you have to do a map lookup to get the slot and then a map lookup to find the offset. And in theory, I believe we should be able to remove these and just use calls or just use inline instructions for this. So I don't know how close we'll get with that, but I think it's promising to look at. And I'll just add also that I think it would also be useful in the general case right now. You have an array with more than 1 element. It'd be nice to use direct access, which isn't supported currently, as far as I know. Let's see, good. I got a few more minutes. Okay, so then in conclusion, this looks promising. I asked, is there any other ideas? I think the lib urcu is a good idea, and look at some of that implementation to see if we can get rid of the EBZ would be great. If there are any other ideas, feel free to put them in the chat. I'm happy to hear ideas about how to make this better. And I'll just mention about the sock hash size. The load balancer case where you're completely controlled from user side seems to be solved by this BPF map iter approach, which is on the list. I think it's under review. I'm not sure if it got merged or not. I think there was a couple small fixes needed still, but that work is going on. I'm convinced it's going to go in. So that solves some cases from the sock hash side, but we still have this case where in Cilium where we have the sock map and we need it to grow. There's another way perhaps to solve this and not use the sock map for policy. You could imagine just not having the map and attaching the policy to the socket directly, similar to how socket local storage works. But as for load balancing and gluing sockets together, you really do need to have some map to point to the right socket that you would like, for example, for load balancing reasons. So it doesn't go away completely, but maybe for a policy, you could do something similar to what local socket storage is doing. Local socket storage and sock map, sock hash were developed roughly at the same time, so they there wasn't too much, ideas being shared across the two at the time. think it's worth going back to look and see what we can sort of, how we can glue those a little closer together. Okay, and with that, I'll just give you a quick conclusion. So we went through the hash resize. It looks like we have useful performance characteristics. I can post an RFC soon, just so folks can start to look at what we talked about here. It does solve a real problem for us. And the bench patches are, I think, useful regardless, just to have out, even if we don't have this hash resize there now, so that we have a way to start looking at the performance characteristics. And there was actually some LRU benchmarks in samples at some point, and I'm not sure where they went. I didn't spend too much time trying to track them down because I just implemented something in the bench framework, but maybe they're still there and I just missed them. But I saw some commit messages, or I had a vague recollection that there was an LRU performance test by maybe Martin or somebody, but I lost track of it. Then on the array resize, it looks promising, and it also has the benefit of not requiring kernel changes, so it should work back to 4.19 or 4.14 even perhaps. And then last, the BPF map type sock map should benefit from these. It's probably the lower priority for me right now because we are generally doing okay sizing those at the moment. Okay, and with that, looks like I have a couple minutes. If there's any questions, I'm happy to take them.
Hey, John. Thanks for the presentation. Could you go to the sock map iterator slide where you kind of say that it's kind of not applicable? Could you explain a little bit more?
Yeah. Okay. So for the load balancer case, it's clear to me how this is useful. But for the Cilium case, what we're doing is we're taking every socket and putting it in a map. So, and we're doing it from the sock ops side. So it's not clear to me how the iterator can not miss sockets, right? Does that make sense? Like if you were trying to grow it by doing a copy from one sock hash to the next sock hash,
Yeah.
Will the iterator miss sockets as it's iterating through is what I'm asking.
I think it will. So, I mean,
Right.
I'm kind of trying to implement it at the moment, but it will. But my question is, could you kind of have a mode where you, I guess the sock ops side inserts into two sock maps, the old one and the new one, and then kind of concurrently you copy via a helper that's invoked from user space. I don't know if that will work at all.
Yeah, like so inside the RCU side, there's this notion of a future table, at least on the lib side. I haven't looked at the lib URCU, but there's a notion of a future table and the current table. So you could do a similar thing, right, where flip the bit so that all sock ops go into the future table once it's created, and then have the iterator come through and clean everything up and move it over. I think that's actually might be workable. I just didn't have time to do much in this space, and to be honest, I looked at the BPF map iterator patches, but I haven't reviewed them close enough to see how to make that work for us in the sock map case, which I think I should do here.
So I'm currently working on that so we can coordinate, because we also want them to copy the sock map, as you know.
Cool. Yeah, sounds great. There was a comment on the chat here. For hash map, can we do partial pre-alloc and grow the free list asynchronously when needed? I think so. So you need to grow the buckets as well, right? So I think this is very close to what the I think it's very close to what the lib rhash table implementation does and what I implemented for BPF. So when you do the resize, you want to create more buckets as well. Otherwise, your hash function will no longer be good, right? And there's a thread that does the allocation sort of on the side asynchronously, which are then added to your free list. And that's one of the improvements between the lib R hash table and then the one I did for BPF specifically is that we used the push pop of the free list and the extra elements, which the generic version has no idea about, obviously. But I'm not sure if that answered the question, but I think it's close. But I'm happy to look at it.
Yeah, we are out of time, unfortunately, so we can continue that on the mailing list. I think that would be useful. I'll now add the next presentation. All right, and I'll make Eric the presenter. So you have the stage, Eric. Please go ahead. You're still on mute.
Hello, everybody. Is my audio working now?
Working perfect.
Great, thank you. Connor, would you like to share your screen and get going?
Yep, I can do that. I will need the presenter though.
I just made you presenter, so.
Ah, thank you. Okay. All right, good to go.
All right, so Connor and I are gonna talk about how we built Magic Transit. A quick overview of this talk. We're gonna talk about who we are real fast, a little bit about the company Cloudflare that we work for, what Magic Transit actually is, how we designed the product, and then get into how we made it work. And finally, some time for questions. So first up, who are we? There's a couple ways to answer this question. First of all, there's myself. I'm Eric Heine. I work at Cloudflare. I've been there for about 2 years. And prior to that, I worked in a few, in some research for security and working at an ISP doing really weird stuff with Linux networking.
Hi, and I'm Connor Jones. I've been at Cloudflare for about 4 months, but I've been in the DDoS mitigation and networking space for around the last 3 years. And I just recently graduated from the University of Michigan.
There's another way to answer that question, who are we, which is the team that built Magic Transit. Connor and I are here representing quite a few people. There's the team that actually is called the Magic Transit team, but there's several other engineering teams within Cloudflare that worked to make this product happen, as well as customer-facing folks such as support and sales and project management. All told, probably 100 people worked on this project in some capacity, and it's been quite the collaborative effort. And it's been, I want to call out those people for their help. Next slide, people, please. Who is Cloudflare? Well, Cloudflare is on a mission of helping build a better internet. And we do this by protecting and accelerating internet applications without adding any extra hardware or installing software or changing a line of code. All the traffic from web properties flows through Cloudflare rather than direct to server. And we do this by operating a global Anycast network. We have data centers in over 200 cities, and we connect with something like 8,800 different networks and see a total of 1 billion unique IP addresses every day. And we provide these services such as DDoS, DNS, Spectrum, at several layers of the networking stack. DDoS operates largely at layer 3, and we have layer 4 products such as DNS and Spectrum, which is a proxy product for generic UDP and TCP traffic, as well as our classic content delivery network and other layer 7 products such as our web application firewall and our serverless product called Workers. What does this look like in the world? Well, without Cloudflare, customers who are running, say, a website have their servers and they have their customers, and their customers send an HTTP request to the internet, goes to the server, which replies directly to them to get the content. When you introduce Cloudflare into the mix, We have our edge network that broadcasts our IPs over Anycast and tracks the customer, the client, the web browser, we call them eyeballs, to the nearest data center. And so when they request a page, instead of going direct to the customer's servers, it goes to the Cloudflare edge. And if it's cacheable content or something that we serve via workers or whatnot, it's just we respond and the eyeball is happy. If it's not a cacheable content or otherwise needs to interact with the origin server, we proxy the request. We open a new connection back to the origin server, and it replies back through the stack to the eyeball. Since this is Anycast, I'm going to describe that real quick in case you're not familiar. The multiple people all around the world may be wanting to look at this web page, and Anycast broadcasts all of the IPs that serve these web pages from all of our edge servers. BGP then figures it out, so to speak, and the nearest network speaking, the nearest data center is where any given eyeball traffic will go to, and this allows us to serve content extremely quickly. Unfortunately, there are also bad folks out there in the world who want to cause havoc. They send attacks, in this case a DDoS attack from this devil who's sending a bunch of traffic from a bunch of locations, and so it's hitting all of our Cloudflare edge. This allows us to handle big volume, but also allows us to not spend a lot of processing time at any given server for blocking this traffic, but we do block it. And when we block it, it does not block the customer's good traffic. We scrub it, and this makes attackers sad, but keeps our customers happy. So our customers were pretty happy with our product, and they started asking us, can you do this with all of my traffic? Previously, before Magic Transit, we had only done proxying products, and now they're asking us to do it with all of their traffic. And we wanted to find out a little bit why they would like to do this. So we asked them, or we asked around, and we found out that they'd like to consolidate vendors instead of paying for DDoS scrubbing from one vendor and all of this layer 7 protection and acceleration from us. They'd just like to have a single vendor. It turns out having a lot of boxes in your premises to do various protection can become a maintenance and operations headache, and customers would love to just pay somebody else to deal with it, and that's us. And so we're putting the network functions in the network and taking away this burden from our customers. And finally, we already offer so much. Why do we want to move down the stack? Well, proxying is not always the answer. There's plenty of protocols out there, for example, VoIP, that just don't proxy well, and customers would still like to be protected, even though it's not a proxyable product. So we decided to, we talked about it and we said, yeah, sure, we can do this. A bunch of our DDoS operations, a bunch of our DDoS protections operate at layer 3 already. We have a giant network. We can handle the traffic. That's not going to be a problem. Why don't we build you a Magic Transit and make that happen? So what is Magic Transit? Quick overview, Magic Transit is our network functions as a service product. We're providing DDoS protection and firewalling without needing extra boxes in your network. And we do this by leveraging our existing DDoS solution that I already mentioned. And one detail that's kind of important is that we advertise our customers' IPs from the edge. We call it BYOP, bring your own IP, via BGP. Prior to Magic Transit, our customer is just pointed DNS at Cloudflare IPs instead of their origin network. So this represents a change a little bit in the way we operate for Magic Transit. Next slide, please. I'm going to pass off to Connor real fast to describe this and how it works with Magic Transit.
Thanks, Eric. So here's the same picture we had before. On the left, we have our eyeballs, and on the right, we have our origins. Notice how it's a router now rather than a server. I'll get into why that's a difference in a second. But a corollary to layer 7, our eyeballs send us IP packets to Cloudflare. We apply Magic Transit. We GRE encapsulate these packets and then forward them to our customer router, where the packets are decapsulated and then forwarded to the customer's infrastructure, which generates a reply and sends it directly to our eyeballs using DSR, a direct server return. And this is Magic Transit in a nutshell. And just like at layer 7, At layer 3, there are still attackers, and we still mitigate these attacks, and the attackers are still sad. Back to you, Eric.
Thanks, Connor. So I'm going to talk a little bit about designing the product. First of all, I'm just going to talk about how we came up with a proof of concept. We didn't want to start building a pile of code only to find out this wouldn't work. So that leads us to our first real design questions is, will this even work? Our product manager came to us with the outlines of what Connor just explained and asked us, can we build this? Can we make this happen for our customers? And immediately I had a bunch of questions. Does GRE actually work that way? The RFCs suggest yes, it does, but implementation details may be something that doesn't allow the GRE from the Anycast to edge like that. Does it scale? Even if it's possible, will it break our other services by using too much CPU or something? And finally, how do we fit it into our existing platform? That last one is a bit of a challenge, so I'd like to dive deeper. Next slide, please. So this is a sort of architectural overview of how Cloudflare POPs operate. We like to keep them very simple. There's an internet connection or several, depending on the particular POP, connects to a router, which then sends any traffic that comes in destined for us to these servers, which we call metals. It's important to note that we don't like to put too much functionality into our routers. We like to keep them simple, and we ECMP balance the traffic and a couple other little router functions, but do most of the processing on our metals, on our servers. The servers are all running all of our software. This is something that we're pretty proud of. We just make it simple. Every server is the same. This also presents a little bit of a challenge for us because every server is the same. So next slide, please. That makes us think of the metal as a router. Previously, all of these servers were just proxying traffic or serving traffic proxying traffic or serving responses directly. And now we're turning it into a router because we're forwarding packets, not just processing them. And so this makes us ask questions like, is the network stack tuned in a way that's going to cause problems? Will these interact correctly, etc.? This is exacerbated by the uniform server thing that I explained, because we have to have both forwarding functions and serving functions on the same box. Some other design challenges that we identified and focused on were customer isolation. We don't want to send packets from one customer to another customer unless that's their intent. We don't want to mess up and accidentally give information out about our customers. Similarly, for security, we don't want to open up new ways to attack our customers by putting them behind Magic Transit. And we want to provide additional security beyond what they normally have, such as DDoS protection. And finally, because we're working on a POC here, we'd like to make sure that the timeline that this takes is not too long enough to prove it out, but not so long that it's a huge project, and that it fits within the skill set that's already available within the company and within the team. And so let's look into some of the technologies we examined to figure out what we're going to do. We looked at VRFs, virtual routing and forwarding functions built into the Linux kernel. We looked at XDP, and we looked at namespaces. Pros and cons of each of them. So for VRF, we were looking at the routing isolation. That's a really nice property of VRFs, and it's a layer 3 isolation, which is great because we're making a layer 3 product. Unfortunately, no one really understood VRFs deeply, and by deeply I mean like, what are the technical details of of IP tables interaction when trying to block traffic for a specific customer in a VRF. Not that it's not known, it's just we didn't have the expertise locally, so we quickly moved on to looking at XDP. Cloudflare in general really likes XDP. We use it for a few things. There's a lot of detail about that on our blog and in some of the other presentations our colleagues are presenting today. The reasons we liked it for Magic Transit is it bypasses a lot of the processing in the network stack, and this simplifies our job quite a bit. I described all the server stuff that happens on these metals, and that involves a lot of IP tables rules, a lot of routing decisions, etc. And this would just bypass it. So that's a real big win. It makes all the stuff we have to do just code. That's also a con, of course, because code is where bugs live. So if we're writing a bunch of code, it's going to cost us a lot of time to make sure that when we put it out to the edge that we're not breaking everything. And so for a proof of concept especially, that was a big con. So we looked at namespaces also. And namespaces are great. They provide isolation in a very deep way. They allow us to use bash and other shell type commands to just make it happen easily. So for prototyping, this was fantastic. And we have a lot of expertise within the company. A lot of people who have used namespaces, a lot of people who know more than just using namespaces, etc. Some of the cons is I've written down here lots of v-eths, but what I really mean by that is that we're creating a bunch of interfaces on the both virtual and real interfaces on real GRE type encapsulation interfaces on the box, and we don't know what that's going to do in terms of performance or if there's just any other scalability problems. And it complicates things. When you traverse namespace boundaries, you have to go through an entire another networking stack in your reasoning about what's happening. But this complexity may or may not be a problem in our evaluation, but we did call it out as this is a thing that we were concerned about. So we had to make this decision. What are we going to do to make this prototype? And we ended up choosing namespaces. The reason we chose namespaces is largely the rapid prototype ability with them. We made a proof of concept in just a few weeks. It was, I think, 4, maybe 5 weeks from starting the project to having a demonstration of the prototype for internal use. And that prototype was a surprisingly small shell script. I think it was like 150 total lines of shell that included not just the solution we ended up going with, but several other candidates. And we measured the performance of this before we finished our proof of concept to make sure it was okay. And it turns out that the data plane performance is pretty good. We were able to forward traffic through the namespace as fast as we could get it to the test box. And so that was pretty promising. Let's just use the scheme that we invented for the whole product. Why not? Data plane performance is good, and let's make it happen. So we designed a product around this concept. Quick overview of that. We ended up choosing to have isolate our customers, having one namespace per customer. This is just the maximum isolation we could imagine providing to our customers. All the traffic is forwarded into the namespaces and then forwarded on to the customers, and we isolate them one per namespace, or one namespace per customer. The way we manage all of this is not shell script anymore, of course. It's a configuration daemon we wrote called Conduit. I like to call it our configurator. It is responsible for tearing down and building namespaces as well as all of the networking within them. It also has the project, the responsibility of managing a small amount of networking in the root namespace, specifically setting routes so that we can get traffic from the root namespace to the customer namespaces. A little bit about this configuration daemon. It's written in Go. Next slide, please, Connor. It's written in Go. We like Go. It has a lot of nice concurrency properties as well as a lot of good tooling. So there's a netlink library out there for Go that is pretty darn good, and we use it heavily. We also use something called Quicksilver. It's our internal key value store that is distributed so that we can write once and get configuration out to our entire edge on the order of seconds to minutes. Yeah, that gives us the ability to rapidly handle changes within networking for our customers' configuration as well as respond to networking conditions. And the final reason we like this design is that this configurator just modifies settings for the Linux kernel. It sets up some routes, sets up some Ethernets and some v-eths, etc. And once that task is done, Conduit can crash but the traffic still flows. The packets are still being forwarded, so we're not dropping customer traffic even if we introduce some bugs while we're designing out and proving out this software. So that's enough meta stuff. Let's have Connor talk about how this thing actually works. So he's going to pull back the curtain a little bit.
Great, thanks, Eric. So now we're going to go behind the curtain of Magic Transit and see how we get packets around. So just as a review, we have our eyeballs on the left, our origins or Cloudflare customers on the right, Cloudflare in the middle. In this case, we're focusing in on a single edge metal. And like we said before, packets arrive at the metal, they get Magic Transited and GRE encapsulated and forwarded to our origin, which responds directly to the eyeball. But now we're going to focus in on that metal in the middle there. And like Eric said, we have one namespace per customer. And the way that we handle the traffic is packets arrive on our NIC, they pass through our XDP pipeline, which is informed by a program called Gatebot, which you can read about on our blog. It's pretty cool. After packets pass that, they get to IP tables, which is where we have some pre-routing rules, and we use IP set matching. So all of our customers give us a authorized prefix in an LOA, which we put into a single IP set. We match all incoming traffic against this IP set and apply a firewall rule mark if it matches. And we use this mark to pick which policy table we're going to route against. So we have a GRE table, which contains all of the routes for our Magic Transit customers. And this routes each authorized prefix to a VETH. These VETHs span customer namespaces, and this is how we get traffic in and out of the namespace. Fun story about these VETHs. Like Eric said, we're going to tell some stories along the way. The outer VETH, sometimes the IP address disappears. So as part of Conduit, we assign IP addresses to each VETH. And occasionally when we do an IP route show, the address is gone. We don't know where it is. We don't know why this happens. So we implemented a quick mitigation, which just runs on a timer, and every X amount of seconds lists the IPs that are associated with this VETH, and checks that against an expected set. And if the sets differ, we add the IP address back to the VETH, and that was the mitigation we came up with for that problem. Also here lives FlowTrackD.
FlowTrackD is an interesting internal product that our DOS team has built. What it does is it watches the connections flowing through Magic Transit and does effectively contracting. But if you recall, we're doing direct server returns, so we only ever see half of the connection, either only the inbound traffic or only the outbound traffic, depending on who initiated the connection. But we still want to be able to do protection against attacks such as ACK floods, which traditionally require connection tracking. FlowTrack essentially hooks into the VETHs using AFXDP, pulls the traffic, pulls all the relevant packets for the customer prefixes, tracks the half of the connection and infers the entire connection state, and finally makes a decision for every packet. Is this part of the connection? If so, forward it, otherwise drop it. This has been pretty successful. We've blocked quite a few ACK floods with this, and so we're pretty happy with it. And there's a blog post that is a couple weeks old now, but announcing that. So if you're really interested, please read up there or contact me, Connor.
Thanks. So after we've traversed this VETH and we've made it through FlowTrackD, we hit NF tables in the namespace. Notice the asymmetry here of using NF tables in the customer namespace rather than IP tables. This was one of the benefits that we got from using namespaces, is that we could go with whatever technology we wanted because we were in our own isolated sandbox. So we didn't have to fit into the rest of the Cloudflare stack. And in these NF tables pre-routing rules is where customers can apply their own firewall rules. So some customers don't want VoIP traffic in their network because they don't want it and they don't need it. Whereas other customers, that's their core business competency. And so they would very much like to have VoIP traffic in their network. And this is where we allow our customers to enforce these rules. Also in these rules are some, in this chain are some rules that Cloudflare provides. One of them being a dummy rule to load the contract module. And the story here is that we were receiving reports from customers that they were seeing lots of IP fragments, but not the first fragment in the chain. And we had traced this back to our firewall rules were dropping the first fragment, but none of the rest of them. And it turned out that we were not doing fragment reassembly within the customer namespace because we didn't have any rules that loaded the contract module. And so we added a dummy rule to NFT to load the contract module and do packet reassembly within the customer namespace. Unfortunately, what that means is when you load contract will allocate a small amount of memory per packet which arrives in the namespace. And the reason this is a problem is because there's a global limit to the amount of memory that you're allowed to allocate. And there's a counter which acts as a safety net to prevent you from hitting that limit. But this counter is reset in every namespace. So you're able to go over the maximum amount of memory pretty easily if you have lots of namespaces. And so we ended up enabling no track here so that we wouldn't allocate that memory. And that's what led to this weird rule in our NFT module, which says load contract, but then also do no track, which as a new engineer to the team, that was kind of baffling, but the story makes it make a lot more sense. So after we've cleared NF tables, we arrive at the routing table within the namespace. And if you read the title of the slide, it says routing tables with an S, second part 1, implying there's a part 2. The part 2 here also comes from a story of having issues with, so the story here is issues with updates. So all of these this route table contains routes for customers to balance their traffic across multiple devices, which I'll get to in a second. But the problem is when customers wanted to make configuration changes to these devices, so they wanted to say add a route, we had this weird thing where when we tried to do IP route show to reconcile the differences, the route wouldn't show up in our IP route show. But we were able to delete the route. And so what we did is we ended up deleting the route, and then we were able to add the route back, which we called this add, delete, add behavior. And we worked through this for a while, trying to reconcile the differences, but it felt a little hacky. And what we ended up doing to mitigate this problem was to construct a new route table that contains the changes the customers wanted to make. And then we changed the policy routing rule to point at this new table to get this sort of atomic swap behavior. And that was the story there. So after we've picked our route or destination from this route table, we hit a GRE device, which does our actual GRE encapsulation of the eyeball packets. Here we're using just Linux devices, which has some nice benefits, such as we can get ECMP load balancing across multiple GRE tunnels. So if our customers wanted to have multiple tunnels and balance across them, this is something we can get just by using the Linux networking stack, which is awesome because we didn't have to implement this and we could offer this as a service to our customers. Another great thing Linux gave us for free was route priorities. So we could set different priorities for different tunnels or allow our customers to do that. And again, these are just great things that the Linux networking stack gave us that we could offer to our customers as a service. And there's another cool story here with these devices, which I'll hand over to Eric, who is muted.
Sorry. Yeah, thank you, Connor. I call this the Magic 3 bug. It's the third thing that we noticed to fix about Magic Transit. Specifically, our GRE endpoints have, as the remote end, the customer's origin network, of course, and at our local end, a IP that's part of the Cloudflare space. It's important to note that the GRE endpoint IP is an Anycast IP, and this provides some interesting issues when generating ICMP responses for, say, fragmentation needed because someone sent a packet that was too large to fit into the GRE tunnel. If we're sending traffic out to the internet and it's sourced from an Anycast IP, this means that we don't actually provide useful debugging information about where the problem may be occurring if it's occurring within Cloudflare's network. So we decided we should send a public IP that's unique to the metal itself, and we're doing that now. We're replying with the public IPs when we need ICMP messages to come from the customer namespace. The problem here is that how do we get a publicly routable IP into the customer namespace without wasting IPs? There's kind of an IP shortage these days, and we didn't want to be wasteful. So we thought, let's use NAT. Unfortunately, that involves contract, and as Connor just went through, we weren't sure if that would cause even more problems for ourselves by using contract. And so we came up with a solution that is to attach the Metals public IP to the VETH inside the namespace, and then use that as the source of ICMP messages. Unfortunately, this means that now the customer namespace can't talk to the root namespace, because any traffic going to the root namespace's IP will be caught by the local delivery route on the IP that's attached to the VETH. So we dropped that local delivery route when we attach the IP to the VETH. This works. We can now send traffic from the Metal IP even though we're inside the customer namespace. However, every time we change anything about the networking settings inside the namespace, that local delivery route either comes back or the IP disappears off of the VETH. So we have to pull it off and reattach it every time. And so that's a little bit weird. We're not sure if that's a good thing to be doing or not. So feedback would be welcome. One last detail here is that we were sending this traffic from the namespace and it wasn't being delivered off box into the internet, and we realized that we had to set this cool sysctl called accept local in the root namespace on the VETH to allow this to happen. So that's the story of Magic 3.
Thanks, Eric. So we're going to go back to just focusing on a single device just for simplicity. So after our packets have been encapsulated, they hit our route tables again, and they hit a default route which says to go to the VETH. But before getting to the VETH, they have to pass through some NF tables post routing rules that we've added, which could include things like dropping all packets which have a destination within the customer authorized prefix, because that would cause a routing loop, which was most definitely a proactive change and not a reactive change. We definitely didn't have that happen. So after we've cleared NF tables, we traverse the VETHs, we hit the route table in the root namespace, we had a default route which goes through IP tables post routing rules to the NIC and then off to our origin. And that's most of how Magic Transit works. And now that we understand the system, we can understand some things that go wrong, such as bricking a metal. So when we were first developing Magic Transit and pushing changes to our edge to configure Magic Transit, we were making changes in the root namespace and in the customer namespaces. And the problem is that sometimes when you make things in the root namespace, code has bugs, things break, and we bricked a metal just by changing things in the root namespace and took down all of the other Cloudflare services that were running on this box. And so the way that we came up with to mitigate that is by using a slow loop, fast loop pattern, meaning any changes which affect the root namespace or resources provisioned within the root namespace happen on a slow loop, which is an order of hours and is on a predictable rate that SRE is aware of. And our fast loop configuration are any changes that happen within the customer namespace that are isolated to just that customer. And that happens as fast as Quicksilver can get the changes out and Conduit can apply them. And now off to Eric for another story.
Yeah, this is one of my favorite parts about building Magic Transit. As Connor mentioned earlier, we do load balancing and we also do route prioritization. This includes health checks, which we use to determine if a tunnel is working correctly or not, and then reprioritize routes for failover and backup, etc. On the fly based on the results of these health checks. And this is per colo. If one POP sees networking connectivity issues to a customer origin, our routes will be reprioritized in that. And this is great. It gives us a lot of flexibility and keeps our customers' traffic flowing even when the internet's having a weird day. The way we did this was we wrote a utility called GREPing. This is one of my favorite pieces of software I've ever written because it sends a packet. The goal is to test that the GRE infrastructure between the metals and the origins is working correctly. And so we send an ICMP echo response down the GRE tunnel where it's unwrapped by the origins router. It sees that the destination is the Cloudflare metal that sent it and just forwards it along and it gets back to the metal, hopefully. If it gets back to the metal, we mark that tunnel as healthy. If the packet is dropped, we start degrading and eventually failing the GRE tunnels. the way we wrote this to do this, to test as much of the path as possible and no more, is that we open a socket that has some unusual socket options, specifically AF packet, SOCDgram, and ETH proto IP as the 3 socket arguments. I didn't even know there was an option for 3 arguments in this at the start of this project, so this is pretty fun. But what that ends up doing is it opens a socket that allows us to send the full IP packet down the GRE tunnel device. And the GRE tunnel device is responsible then for encapsulating the packet with the GRE header and the outer IP wrappers and sending it off to the internet. This allows us to test our end of the infrastructure and the customer's end of the infrastructure and configuration without needing to involve a whole bunch of extra work or without redoing work. If we'd used a regular raw socket, this would not be testing that we've set up GRE correctly, for example. So we're pretty happy that we wrote this, and it was a lot of fun figuring out how to test specifically the thing we were worried about and then do prioritization. So that was a fun one.
Cool. Thanks, Eric. We've got a few open questions on this project, such as disabling TX and RX checksum offloading. So if we leave this on, our throughput goes very, very, very low. So if we have to disable this for Magic Transit, we're not sure what this accomplishes, but we know that if it's on, then we have problems, and if it's off, we have good throughput. Like I mentioned before, the disappearing IPs, would love some feedback on why that is the way that it is. And I see that we have some questions, so hopefully we can talk about that afterwards and maybe figure out what's happening there. The other issue we got into was some ARP stuff. So when developing FlowTrackD, looking at packets that are crossing that VETH, we ran into an issue where we would see a bunch of ARP packets fly across the wire, and traffic would pause for a minute, as in packets would stop flowing while ARP figured out what was happening, and then packets would continue flowing. And so we don't know why this is, but the way that we mitigated it was by adding permanent ARP entries across our interface, because we're provisioning all of the resources, we know what the MAC addresses are going to be, and so we can just add the ARP entries ourselves. And at this time, we'd like to open it up for questions. Thanks for listening.
So in the chat, David Ahern, I hope I'm saying that correctly, mentioned that the VETH shouldn't be dropping addresses. Yeah, we agree. I don't have immediate answer to what IP monitor shows and if it shows a delete or not. I can always follow up with you afterwards on details about this. It's been a little bit, so I have to refresh my brain and maybe do some experimentation based on this. We've had several people looking at this problem, so yeah, it'd be great to coordinate with you. Kevin Mason asks, how's the traffic distributed amongst the metals? We do this at the router. I mentioned that the router has only a few functions. One of them is ECMP load balancing, and so the metals join an ECMP group for the IPs that we distribute for our customers, and it gets balanced across there. How many customers? Oh, go ahead.
Thanks. We support all of our customers on all of our nodes. We have more than 50 Magic Transit customers, and we have all customers on all nodes. Kind of in line with how Cloudflare does the rest of our services, is that we run all services on all metals in all colos. So all of our customers per node.
Yeah, that was one of the concerns we had. Also, is how does this scale with that many namespaces across all of our nodes like that? Sort of our answer is right now it seems to be working really well, and our tests show that we could add several hundred namespaces without a problem, at least in the lab. And so we're going with this for now until it starts showing concerning symptoms, at which point we'll figure out what to do to scale it further if that becomes necessary. Can we share example configs from Metal host? Configs root namespace, one from customer namespace blocks, etc. I'm not sure what we're allowed to share, but if we're allowed to share it, I'd be glad to share that with you. I'll ask the appropriate people if we can how low we can go with the configs, and be glad to get back to you about that. Yes, you did hear that correctly. ICMP echo reply is what the Jerry program, Jerry ping program sends. It's we did that because it turned out it was less common for our customers to forward the ICMP echo reply on our. Let me start saying this sentence again. I already confused myself. We found out that it was more common for our customers to have ICMP replies turned off on their routers, and that they didn't want to turn on the ability to ping their routers. And so this was a way of just saying, look, this just forwards traffic, and the routers are usually configured so that that traffic is forwarded correctly. And that was sort of the big reason for the ICMP echo reply. The other reason is sort of a hand wavy, well, what if ICMP processing is broken on the router? But that's not a realistic concern. It was just another cool thing.
Seems we have one more person typing, so okay. Yeah.
Would it be possible for a bad actor to force traffic to an individual metal, causing too many namespaces to get used? There's a couple parts to that. Forcing traffic to a metal and the path that Magic Transit uses is something that isn't really possible, and I'm not going to get into too many more details about that because that's starting to get into territory that I'm not comfortable pretending to be an expert on. But I do know that forcing traffic to a single metal is pretty difficult the way we've set it up. Yeah, you're welcome. I'm glad to hopefully inspire some cool stuff. Please be in contact if you do end up doing that. I'd love to compare notes on what you discover and what we discovered.
So we have 2 more minutes in case somebody still has a question. Looks like no one is typing. So thanks a lot, guys. Oh, there's one Marche. Let's see what he has, and then.
How many namespaces can a metal handle? I think the largest number we tested with was 1,000. I'm not 100% certain if that's the highest number. It might be higher, but I know for sure that I stopped paying attention to that question after 1,000 because, frankly, if we end up with 1,000 Magic Transit customers, we can engineer whatever solution we want because at that point it's a pretty big product and we can go further with it. And so I can say at least 1,000.
All right, Joe is typing. I think that's the last question we can take. And
Yeah, that's good feedback. It's I'm gonna have to maybe follow up with you and get some more details on that, Joe. Thank you.
you probably have to read out the comment. So basically, Joe says 1,000 sounds plausible. I know sometime back in OVS we hit some issues with number of devices at once in a Linux stack and started hitting problems a bit above that. And there was stuff around how many tunnels you can run, etc. Cool. Yeah, so we're now 1 minute over time. Thanks, guys, for your presentation. And that also concludes the 4th day of the networking and BPF track at LPC here. And I hope to see you all tomorrow at 7 a.m. for the last day, for the last set of talks. Yeah, 7 a.m. Pacific time. Thanks, everyone, and have a good evening or rest of morning. See you.
Thanks, everybody. See y'all.
you.